Okay, it looks like we might not have any chair here, so maybe let's just start with the talk. My name is Mateusz Baran. You may call me Matthias if you prefer. I will talk today about Julia manifolds and our approach to computing and showcase what our ecosystem is currently capable of and what you may expect in the future and why you might care about manifolds at all. Okay, so I will start with a less abstract way of talking about manifolds. If you have ever encountered this concept, it's mostly quite abstract, very difficult math books. I will try to demystify them a little bit here and provide a more straightforward approach. I will highlight two parts of the ecosystem that I think are fairly mature and useful. The first one is Manopt, developed by Rone, who is sitting here with us, and it's a package for optimization on manifolds. And the next part, the next large part of the ecosystem that I think is interesting is statistics on manifolds. The last slide will be the future of the ecosystem. So let's start with why we might care about manifolds at all. First of all, it provides very generic support for complicated data structures that may contain vectors, matrices, structured data, neural networks, whatever you want. And the key part here is that you can develop algorithms in a way that doesn't require flattening those structures into vectors or arrays. You can keep the complicated structure and work on this. You can develop complicated algorithms. Basically, any Manopt optimization algorithm works with any complicated data structure. The second reason to care about manifolds is that they enable a very nice way of handling constraints. If you have some constraints on your data or your model, you may be aware that, for example, you cannot use straightforward Euclidean optimization methods, but you need to introduce constraints which limit what kind of solvers are available. They introduce some penalties to performance. In this approach, if you have a certain kind of constraint, we support, for example, orthogonality constraints, spheres, and lots of other types of constraints. It's not arbitrary. It's not like you can take any constraint and feed it here efficiently, at least. But if your constraint is one of the few that can be easily supported in this way, then you are in luck. You still have access to all the standard tools that are available for unconstrained problems. So we get away with constraints and just replace them with expressing algorithms with special operations. We further reduce numerical issues caused by local parameterizations. You may be aware that another way of, for example, dealing with constraints is you just introduce a parameterization. For example, on a sphere, you may introduce a map that transforms this constraint, for example, optimization problem or optimization or another data analysis on a sphere into analysis on a flat space without any constraints. But this often leads to issues. For example, if we have a sphere, then it's not possible to map it into Euclidean space without removing at least one point from the sphere, right? So if you have data that is all around the sphere, you may have severe numerical issues when you reach the limit of your map. The way we solve the problem of constraints, or constraints in manifolds, JL and Julia manifolds, completely removes this problem, because we try to minimize the amount of computation that is done with parameterizations. We have a generic interface that doesn't require introducing such parameterization. Next point is that manifold-based algorithms allow for respecting the geometry of your data. For example, if you have data on a sphere, then it's not a flat space. It has certain curvature, and handling this curvature in, for example, a statistical model may result in having a model that is more appropriate for your data. Okay, and last point, sometimes you may already use manifolds for something. For example, they are fairly popular in physics, but also in robotics, for example. They are also quite heavily used, especially Lie groups, which Ron will be talking about in a moment. Okay, so let's talk about what a manifold actually is. A manifold is basically any set. We don't have many restrictions on what this set is. We need to specify a certain number that is the dimension of the manifold, and it basically tells how many continuous parameters this set has. So, for example, if you have standard d-dimensional Euclidean space, then this is the dimension of this Euclidean manifold. For example, a plane has 2 dimensions, a straight line has 1 dimension, so that's fairly intuitive. A standard sphere has 2 dimensions, because we need to specify 2 coordinates to identify a point on a sphere. Next part that is required is a collection of charts. So this is basically what I was talking about, the way of removing constraint by introducing a chart and mapping everything into Euclidean space. This is the condition that says that we can do this with a manifold around any point we want. The trick is that here we only require this chart to be defined in a certain neighborhood of each point. It's not a global thing, it's completely local, and we may need multiple charts to cover the entire manifold, and thus we cannot rely on just having one chart. This is why we have the I index here. And those charts provide a local view of the manifold as a standard Euclidean space. So this may be also viewed as a certain kind of local flattening of the manifold. There are also some topological conditions that tell in what kinds of sets and what kinds of structures are disallowed, basically. It's probably the part that is the most challenging from a theoretical point of view when you study manifolds, but it's, I think, not particularly required to know to use Julian manifolds. You may know nothing about topology, and it's okay. I think it's fair to say that topology basically is for restricting certain pathological cases that may appear when you consider the other points, and we just say that some things are not well behaved, and we don't consider them as manifolds. And last part is intrinsic operations. If we only have charts, then we don't we can't do much with manifolds. Intrinsic operations are certain operations on manifold that don't depend on the selection of a chart, basically. That's how we can think about them. And why do we care? Well, we care because charts introduce those not very nice things that they are not global but only local. We want operations to be generally chart-free. This way we don't have to flatten, we don't have to switch charts. It's basically much simpler. I will talk in a moment what operations are available that are intrinsic. This is a fairly large set of operations. Lots of algorithms can be expressed in such an intrinsic way, so it's, I think, quite a good justification to work on manifolds. Here is an example of what are the problems with charts. On the left-hand side, we have a simple manifold, a circle. It's a manifold. We have two charts, phi1 and phi2, and they map the parts of the circle to a 0,1 interval. You can, of course, perform any operations on this interval, but you may notice that those intervals don't cover the entire circle. They have small gaps that are necessary to perform this unwrapping. So that's why it's local. Generally, mathematicians tend to point out that there may be lots of charts needed for standard manifolds that we commonly encounter. We basically need at most 2 charts per connected component. So it's not that many that we have to introduce, but we very often need more than one, and then we need to figure out how to switch between them. And switching is done usually by transition map. So this is how we can switch between one set of parameterizations and another one. Now, what isn't a manifold? Basically, most things kind of are manifolds. So basically, any complicated structure can either be considered a manifold or decomposed into ones with some minor restrictions. Maybe somewhat interesting. For example, a closed interval is not a manifold because it's not at the endpoints locally like a Euclidean space. It is similar to a closed interval. So it is introduced as set of non-negative real numbers a little bit below, and this is why it's not a manifold. And a square also is not a manifold. It's so-called manifold with corners, but those are basically technical issues here. It's not like we cannot work with them with Julia manifolds. That they just present certain challenges that mathematicians tried to sweep under the rug and don't handle. But it's perfectly possible using some additional considerations. One additional known example of a manifold is a plane with a duplicated point. It's a standard example in topology of why the topological conditions are necessary to avoid pathological cases. Basically, if we have 2 points on a manifold, we would like to always be able to separate them using open neighborhoods that are disjoint. If we have a duplicated point on a plane, then this separation is not possible. This causes issues. So that's something we disallow. There are also other counterexamples in topology, but they are often very, very weird, so I will not be talking about them. There are also some generalizations of the concept of manifold that we, to a certain degree, consider. So, for example, we have manifolds with boundary, or manifolds with corners that don't locally look like Euclidean space, but like a Euclidean space times this set of non-negative real numbers, and this way we can handle certain constraints on such sets. Another important concept here are stratified spaces. We currently don't do much with them, but it's on our roadmap to include them in what we support. And they significantly expand the number of things we can do. So let's now talk what are the basic operations that we can have on a manifold. Basic concepts. One of central concepts is the concept of tangent vectors. Tangent vectors basically extend two standard concepts in Euclidean from the Euclidean setting: a velocity of a curve. So if we have a curve, we can compute its derivative and see how fast it's going and in which direction. And another concept that is also expressed by tangent vectors are directional derivatives. So we may have a function, a scalar function on some space, and we may have a direction which points in which we want to calculate directional derivative, and you can also do this using tangent vectors. Okay, this definition is quite technical, but what's important is that basically tangent vectors are those arrows. You can think of them as arrows that point into the direction a curve is going. The definition is quite technical because there are multiple curves that may pass through a point in the same direction, so we have to consider that such a tangent vector may be represented using different curves. But that's not how we usually represent tangent vectors. We usually do it using either numbers in an embedding. That's one most common way, and another way is expressing using coordinates in a certain basis. Sometimes it may come from, for example, some chart, and in a chart it's the most easy to see how it works. Okay, there are many more operations that are that we can introduce on a manifold. Them here in a certain in a few certain categories. The basic structure that we have just talked about is the topological structure, but we also can have, for example, a way to calculate volumes on a manifold. It's one additional structure. It's a key part if we want to introduce densities on a manifold. For example, for statistics, we have an affine connection, which is another important part if we want to relate tangent vectors at different points to each other. We have the triangulations, but this is not something that we work much on Julia manifolds. It's something I'm thinking about doing at some point, but not right now. We have group operations, which lead to Lie groups from the next talk. We have a symplectic form, which is sort of important in some physical applications because it can connect Hamiltonian of a system with the tangent vector along which an object is evolving. We have finally the inner product, which is the central point of the Riemannian geometry, and I have also written distance there. It's not particularly well known thing, but you can generalize Riemannian manifolds to allow for more complicated ways of calculating distances between points, and it also mostly works. The arrows basically are there to point out which concepts are more specific. So, for example, if we have a group operation, then it implies that there should be a certain compatible affine connection and density on a manifold. If we have an inner product, it implies a certain standard symplectic form, certain way of calculating distances, and an affine connection as well to connect different tangent spaces. Affine connection is basically the central thing that we need to be able to do much with a manifold. I think it's not very well introduced in most books, at least if we want to do some computations. It's actually a fairly simple concept if you know ordinary differential equations, because it's basically just a system of ordinary differential equations on a manifold, which allows you to transport tangent vectors at one point to tangent vectors on another point. This, for example, is useful if you want to calculate geodesic. So you start in one point on a manifold, you have a tangent vector, so you know that you want to go in roughly this direction, and without an affine connection you wouldn't know how to go further. If you want to, if you picked one curve, then if it would go one direction, another curve, another direction, it doesn't specify which direction should be chosen. This is done by an affine connection. This leads to the concept of exponential map, which is basically how we move from one point in another direction. We have a logarithmic map, which does the opposite. We have a distance concept on manifolds, where we can calculate distance between two different points. If they are connected by a geodesic, we have an inner product on manifolds that basically enables us to generalize most standard algorithms to manifolds. But the key part here is that we do not need charts to do most of these computations. Julia manifolds basically collects all algorithms, all the different algorithms that can work in this way. We have a fairly large ecosystem. We support lots of different manifolds. We have, for example, man-up-to-jail, which I think is interesting. It is a package for nonlinear optimization. We have support for link groups, which is very important for robotics. We have a lightweight interface package. If you want to do something on manifolds, you may just depend on a fairly lightweight package to do this. We have support for differential equations on manifolds. This is one part where I think SciML is not really not having all state-of-the-art solvers. For example, link group solvers in SciML are fairly limited in what they can do. Here they are fully generic. You can do them for whatever they are capable, and they basically generalize standard Euclidean solvers for certain ODEs. And I think the one important part for this is that you can solve certain algebraic differential equations without having to worry about constraints. You just turn constraints into geometry using this approach. And there are also a few work in progress things. Here is an overview how to do all those things in manifolds.jl. I will share those slides later. I think we don't have enough time to go over this, but one important thing here about our interface design is that all operations that we implement have manifold as the first object in a call, so that way you know what we are working with, and all other points and tangent vectors are type unconstrained. We can represent those concepts using any type we need. They can be static arrays, standard arrays, array partitions, whatever. And here is a small example of how we can generalize a standard Euclidean algorithm to manifolds. You can, for example, have Hermite interpolation that looks fairly similar to what is done on Euclidean manifolds, but using Julian manifolds, you can easily generalize to anything. For example, you have logarithmic and exponential map here, which are usually fairly easy to find out for your manifold, but there is also differential of the log for with respect to argument, and this is something that is usually more complicated to find out. We have that for many manifolds. Okay. Manoff will be in the poster session, so maybe we'll leave it to there. Also, a few words about statistics on manifolds. This is also something that has seen a lot of development. There are a few different external packages that developed those concepts. We have, for example, one package by Julia Robotics that uses it for inference in their solvers. And we also have a very new package that does Kalman filters on manifolds in a very generic way. And it basically shows that you can work with Kalman filters on very generic spaces. In the future, we'll surely add more manifolds. We have some ideas to add branch and bound things to our library. We will improve support for manifolds with corners, so that basically anything that is continuous like would work here. There are some performance improvements to be made also. Our approach is basically make as much as possible work correctly and optimize what is necessary to be fast. So there are some things that could be faster. We have lots of ideas to develop, so I think it's a very active set of packages that is being developed here. And we have also a paper that you may read if you are interested. Okay, I think that we are out of time right now, so I will stop here.
I think we have time for one question. I'll Martin get set up. There are 2 questions. And thank you, Matthias, for that talk. Thank you very much. Question? Yeah.
So not exactly a programming question, but since this is actually relevant to like my research, When we talk about tangent spaces as like being velocity of curves versus like the differential operators in some directions, you've mentioned how they're basically the same notion in finite dimensions but not in infinite dimensions. Is there like a way of describing that difference, or is that a bit too complicated to answer?
Okay, so the difference between finite and infinite dimensions in this case, it's fairly complicated. I think it's mostly technical and not something we need to worry about. I just also have done some work with infinite dimensional manifolds, and there is also some complications that you may have directional derivatives that are very weird in a way that they don't point in any direction. But it's very theoretical. This is another example of mathematicians considering very exotic things, and they don't really have much practical application. But I think it's quite interesting that such things appear in theory.
And also in practice, at some point, you have to discretize. So, I mean, to get it to numbers, something infinite dimension, you have to approximate by a finite amount of points or something. Yeah. Definitely something that we want to cover, but maybe also someone that has to come along and say, I need this, can you help me? So that's sometimes also just driven by that.
Awesome. Thank you.
Thank you, Matthias. Next up, we have Ronnie Bergman with groups and smooth geometry using legroups.jl.
Thanks for the nice introduction, and thanks for everyone coming here. Yes, I want to talk about something that is new in the Julia manifolds area, namely legroups.jl. You can find the slides already on this QR code if you want to follow along on your own screen. Yeah, so let's get started. So our problem might be that we have data that is, for me, the first one where I counted that is rotation matrices, but maybe also invertible matrices, or something like rigid body motions somewhere. And the problem with those data, if you have those, or you want to, I'm an optimizer, so I want to maybe find the best rotation matrix to accomplish something. Then I have a cost that depends on my rotation matrix. And if I want to do a gradient descent, the problem with those is they are non-Euclidean. What do I mean by that? Well, you can't just add two of those. So one of the basic things we learn in primary school, plus, is no longer allowed. That's the regime we're in. But we have a lot of structure we can use for these three especially. Namely, well, they informally phrased, I tried to start informally, they have a certain neighborhood, so around every point I can find a certain environment of rotation matrices that are kind of close by. And I can maybe even talk about what dimensions or how many degrees of freedom do I have to move. And the last one is they have a group operation, so I can always multiply two rotation matrices and still get a rotation matrix. And I can define something like that. I mean, invertible matrices is also just matrix multiplication. But for rigid body motions, so translation and rotation, I can do something similar. So I can define what is a group operation to work on those and stay on those. Okay, so the goal for today is to look a bit into that and look how we can model that in code, or also to look at which ones do we currently already cover in the package I want to talk about, legroups.jl. Okay, let's dive shortly into history. So I came to Julia in 2016, or shortly before that maybe, and wrote manop.jl to do optimization on Riemannian manifolds, slightly different. And the day I released it on a forum, there were 3 people coming by and saying, that's nice that you do manop optimization in manifolds. Can we also just do manifolds? So we started manifolds.jl. That was released in 2020 and already contains something that I want to come back to later, namely the group manifold. And last year we decided to start legroups.jl, so an interface or a library of legroups. And kudos to Hua2, who gave us the package name. So he started that, but didn't really follow up. And he was kind enough to hand over the package so we could continue that and now call our package legroups.jl. So kudos for that. Yes. For the whole overview on what we can do with manifolds and Julia manifolds, there was just a talk by Matthias Baran that you maybe were already here or missed. If you missed it, you have to watch that maybe later online. Okay, so first question, what's a manifold? Something that locally looks like RD, where D is a fixed number. And the easiest is, again, the sphere, so the Earth we live on. Okay, the Earth looks more like a potato, but maybe have in mind it looks like a sphere. Then locally, it's a two-dimensional thing. I can always move north-south, and I can always move east-west. But globally, it's not just R2. It's more complicated, because if I walk long enough, I come back to my starting point. So that's definitely something non-Euclidean. And I also can't just add points. If I add 2 unit norm points, I again leave the manifold. The second example would be 2D rotations. I try to stick with the easiest ones. Locally, I can just change my rotation angle a bit, so that's nearly a line. But if I rotate by 2 pi, I'm back at my starting point, so that's definitely not the real line that I'm facing. Or the last one, if I do that in 3D, then I prefer to write that as matrices, where RT, R is the identity, and the determinant is +1. You could do that in Euler angles or in German Euler angles, but then you have the disadvantage you don't have a unique representation, so there are different parameters that represent the same thing. So that's why I like to stick to rotation matrices. But they locally have 3 degrees of freedom, so you can move in 3 directions, maybe rotation X, rotation Y, and rotation Z. So that's 3 examples of manifolds that we need in the following. And then the next thing we need is a group operation. So maybe you've seen that in an introduction to linear algebra or something like that. So this defines a group. Namely, I have an operation that couples 2 elements on my set M, the manifold, and gives me a set M back with a few properties. Kind of like I have a neutral element E that does nothing to my objects. I always have an inverse element, and if it's abelian, I even can arrange, do A times B or B times A. So those things we need. Okay, and that's all ingredients. So if the group operation as a map from the Lie group, from the manifold times manifold to itself, and this inverse operation, A to its inverse, are smooth maps, and we have a manifold, as on the last slide a bit informally introduced, then we call the whole thing a Lie group. That's what I want to talk about. In really this abstract setting. So also the software should model this abstract so that it works with any Lie group you come along. I've seen now one issue or pull request that has a quite complicated Lie group already. But we want to model that in the abstract sense, so any Lie group you come along with, we want to cover that numerically, hopefully. Okay, and usually, so quite often, these are just n by n matrices. The multiplication, the group operation is the matrix multiplication. But then you have to have in mind, well, we need an inverse. So both of them have to be definitely invertible, or we have to be in the general linear group. So all invertible n by n matrices. That might be some set that we often work on, but not always. Okay, short history. So the groups come from Niels Henrik Abel. The manifolds come from Bernhard Riemann. And then Lie groups were studied to find symmetries in differential equations, and that was Marius Sophos Lie, and that's also the name giver of Lie groups, and hence our package. Why am I mentioning that? Well, I'm at NTNU in Trondheim in Norway, and both Abel and Lie are Norwegians, so sorry I had to mention that. Okay, the next thing we need is what I would usually call looking directions, or finding derivatives of functions in the end even, or using that for that. So if we take any curve that runs through our rotation matrices, so it runs along on rotation matrices, that runs at time 0 through a point G on our Lie group, then we could consider this C dot, the derivative of that curve, as a looking direction. Just imagine on the sphere, one curve again, you're at a point, you look at the derivative, that's a tangent vector, and you could interpret that I'm standing somewhere and I'm looking into a certain direction. Okay, that's not the full story. Formally, we have to build the equivalence class of all curves that have the same derivative, but then we end up with X, and that's called the tangent vector, and if I collect all of those, I get the tangent space at a point. That's basically collecting all looking directions, collecting all derivatives. And there's one special case that I need in the following, so it even gets this frac G as a symbol. That's the tangent space at the identity E. So we always have the group operation and the identity, so we can look at TEG. That's called the Lie algebra. That's a very specific one. Also note that this tangent space, I even call the x's already tangent vectors. That's a vector space. So we suddenly have plus again. That's nice. In every tangent space. Okay, so much for that. Small detour. To get a Riemannian manifold, we need an inner product on each of these tangent spaces that smoothly varies in G. But then we have maybe the small disadvantage, or the one additional thing to have in mind. We have a whole family of inner products on each of the tangent spaces. Maybe we don't want to fully do that, or maybe we want to simplify that using our group operation in the following. So that's maybe something to have in mind compared to Riemannian manifolds, which is not the focus of my talk today. Okay, let's look at a bit of code. So here I plotted maybe the old way to do that, or to phrase that in manifolds.jl. So we take the set of rotation matrices, but now have in mind that's still without the group operation. It's really just the set of matrices where R transpose R is the identity and the determinant is 1. Because it could also be -1, so we want to exclude that. Then I could just generate a random point G, say, oh, I want to have the one element on these matrices, that gives me the unit matrix. I can check that that's a point. G plus E is not a point, because I can't do plus on those. And G times E, well, we do a group operation here, but a bit implicitly, is on my manifold, so that is again true. And if I want to call the inner product, I always have to specify the manifold, the point I'm at, and then that's exactly the inner product at this point that I'm computing. Okay, if we switch to Lie groups, a few names change, but a few things get a bit nicer. So this is the switch to Lie groups. The Lie group G is called the special orthogonal group, but that's the rotations with matrix multiplication. The manifold dimension stays the same and actually passes through to manifolds.jl. E now gets its specific name, it's the identity element. So that way you can even exchange the G up front and do the same thing on another Lie group. It's a point on my Lie group. I have composed, that's the group operation now, also very generically implemented. And I can use frac G, the Lie algebra, and then I can just compute inner products on the Lie algebra. I don't have to specify the E explicitly. If you want to think in allocations, on the last slide I had to allocate the identity. Here I don't. So we spare that a bit, and it gets a bit nicer memory-wise. Okay, so much for a little bit of first code. So then the small technical detour we still need. If we have considered the group operation, multiply with G from the left, we can look at its differential. That would then suddenly map from one tangent space to the next. But it's even a bit better. It allows me to identify these tangent spaces and say, well, if I have a vector field that maps from my Lie group, at every point I get a tangent vector, so that's a vector field on my Lie group. Then this vector field is called left invariant if this equality holds. In other words, the differential already determines what the values at other points are. What's the trick here? If I know it at one point, I know it everywhere. So it's maybe even enough to know it at the identity. Then I can use the property from above to know my vector field anywhere. Or one vector is enough to know the whole vector field. An example would be, well, the simplest one, real line with plus. Then we have a constant vector field. So it's basically generalizing constant vector fields. And if I take SON, then I always just have to basically rotate my tangent vector to fit. So it's G times X, where G is a rotation matrix. So that way, I can identify tangent vectors in an easy way, or even just take the one at the identity, because I just have to multiply by G to know the one in the specific tangent space. That's now because I have the group operation. That's what I can use. In Lie groups, there's diff left composed to exactly compute this differential that we need here. Okay, so since we know that this is true, that we have a point in the Lie algebra, then we know what the corresponding invariant vector field does in the point G. We can use that to just know it at the identity, because we could always, for the rotation matrices, just multiply with G to get to the right tangent space. So we can just omit that because the whole thing we can do now is to define the inner product at a point G, we can just move everything back with G inverse to the identity and do the inner product there. So we just have to remember one inner product on the Lie algebra. Or even better, we can even omit storing y and z, and we just store these G inverse y and G inverse z, because that's basically the tangent vector everywhere. Then I can always spare this multiplication with the inverse. Okay, so that's easier, and we usually even represent tangent vectors by the Lie algebra elements, because that's a bit easier on Lie groups compared to manifolds where we don't have that choice. Okay, then we want to walk around. So we talked about looking directions. What if I want to walk that way? And there's one nice definition on Lie groups, namely the Lie group exponential. And that just says, let's take a curve that realizes the left invariant vector field. So gamma of t is a point on my Lie group, times x should be the derivative. That's really just what does walking around with this x mean for the vector field. I want to start at the identity with the right direction, and then I evaluate at 1. So that's how I can walk around on a Lie group, because I just compute this ODE, evaluate at 1, and then I get my Lie group exponential function. Okay, so now we have a way that replaces plus, because now I'm suddenly standing at a point, I have a looking direction, and I can walk there. Took us half my talk. Okay, so on Rn, it's really just the exponential is just x, because from 0 going x is just plus x, 0 plus x is just x. And on the circle, we get the complex exponential. And for SON, we get the matrix exponential. So that's how we would start from the identity walking somewhere. Now with the exponential, you have to be a bit careful, and that was one of the caveats when we started redesigning and started with Lie groups now. There's a bit too many names that are called exp. So there's the Lie group function that we just had on the last slide, where I have, you see the code on the side, g and x given. And I want to go somewhere. You can do that in place in G with the exclamation mark function. So that's the Lie group function. Now you can have the one that says, I want to start at G and walk somewhere, maybe to H. So that's the Lie group map. But those are two different functions, and they work a bit differently. They have a bit of a different signature. And then I have to be careful, because also the Riemannian manifolds have something that's called geodesics, acceleration-free curves, and which, with respect to the Riemannian metric. So there's also exponential map on a manifold from a point G in direction x. So be careful if you see exp, because they have these three different meanings. You always have to check a bit which one is which. And of course, if you're not in Julia manifolds to L, Lie groups to L, there's of course also just x with one parameter, which is either the exponential or the metric exponential, right? So if you have just one parameter, forget all these, and you're just in the classical linear algebra case. Okay, so that's the caveat with the exponential map. So let's continue with the code example. If we now, again, stick to the special orthogonal group, then we want to take 2 points. Again, use compose, maybe even in place if you want to spare a bit of time. With the inverse, then we get back. And finally, if we're on the Lie algebra, we can also do the exponential map into a certain direction. That's a point on my rotations matrix, Lie group. And I can do log, that's the inverse, and I get back the same point. So that's, again, a few functions we can use and work with. Okay, so finally, we need Lie group actions. So again, for rotation matrices, how do they affect the vectors? So we could have G is the rotation matrix, and, oh, that's 1 to 4. G is SO3 and M is just R3. Then the action describes what's happening to my vectors if I actually apply the rotation. That's the action. And here in the very generic sense, give me any G, Lie group, M manifold. How does G act on M? That's an action. Now, the first thing I can define without even the action in mind is product Lie groups. So the first and second component, I always think of arrays. The first is a rotation. The second is maybe just Rn. then we get product Lie groups. We have that just with the times operator implemented in Lie groups.jl. And the other one is semi-direct product Lie groups, where the second component has a certain coupling. So they don't have just H grouped with H2, H1 with H2, but there's the action of G1 acting on H2, and then only we do the group operation. That's the semi-direct one. So the first one is direct group operation. The second one is semi-direct in the right-hand side, and that's the L times operator G, L times H. And you can do that the other way around. Switch those two and you have the right semi-direct product. With that, we can define the special Euclidean group, SEN, and it just works as the Lie group, but it's a bit more complicated in all its implementations. So that's usually an array partition where the first component is a rotation matrix and the second one is then a vector of the corresponding length. So here SO2. Oh yeah, this one I shortened to SO2, no, SO3. Then there's maybe a number missing in the end that we can store and work with. But then all other functions work the same way. And we can, again, use log to get to the Lie algebra. And one thing that people then often want, I mean, the Lie algebra one is a certain skew-symmetric matrix. If you want to get that into something that's really just three-dimensional, then you use V to get a representation in coordinates, basically. OK, so one other thing, if you work with that and things go wrong, it's usually nice to have something that tells you when is it going wrong and why. That's the validation Lie group. So you can easily wrap your Lie group in a validation Lie group, and then it would error as soon as something is no longer on the Lie group or no longer on the Lie algebra. Automatically, every input gets checked, every output gets checked. And you can even change that to, instead of error, please only warn. And you can exclude either functions or certain contexts. So if you don't want to check inputs, only outputs, then you set the ignore context of input to input, or if you want to exclude any checks for the exponential map, you set that one. Okay, let's do a short overview of functions that we currently have. We talked about compose. Besides that, you have adjoint and conjugate. Exp and log, of course, we had those two. You have a lot of combinations, so inf left compose, inf right compose. They might spare time compared to first computing the inverse and then compose, and differentials of all these. We have the Jacobian conjugate, so that's the differential of the conjugate, and the identity element we already had as well. On the Lie algebra, we of course can get back the Lie group it's based on. We can get coordinates and reproduce the vector from coordinates. We have the inner product, and we can get a zero vector for now. Okay, and all of those also work in place, where you would provide the return value as second argument, and then you might spare some allocations again to be more efficient. And quite a few functions that are just passed through to the manifold. So behind the Lie group, we always have the manifold. Okay, a notable difference to maybe group manifolds real quick. Yes, there we had xbli for the Lie group exponential and xinf for the invariant, left invariant exponential map that I talked about. And that we unified in Lie groups.jl. So it was a bit inconsistent, but that was basically developed over a few years. So we used the Lie groups.jl package as a good restart for this one. And we made a full list. If you actually worked with with group manifolds before and want to switch, there's a whole list of everything that we changed. Okay. Now the Lie groups that we have are just power and product. If you have a Lie group, you can build either vectors or tuples of elements. We have the left and the right semi-direct product group that we had. And in Concrete's group, just a few of those. These are the ones currently available. Well, the circle group with 3 variants, mainly for learning stuff. The orthogonal group, special orthogonal, maybe also symplectic. That's symplectic matrices with a metric multiplication that you can work with. We are open to new ideas and further Lie groups to extend that, but that's the current ones we have. Okay, let's summarize. We talked about what are Lie groups and how can we model them, how can we work with them, and how do they work in code. Group actions a bit, because we very generically defined a semi-direct product Lie group. But these all are available, and there's a whole interface, so you can easily define your own Lie group and an action, and then get a semi-direct product if you want to. And we have a whole library of Lie groups, and I hope I always cared about that the formula and the sources where it's from are documented as well. So that's hopefully the case. We might have a few corner cases where this efficiently implemented is not yet fully there because we just started this package half a year ago. But that's roughly what I wanted to summarize here for this one. You can find the documentation on the Julia Manifolds GitHub IO. This is the main literature I used for the talk. So the Manifolds.jl paper, the Man.jl paper, and quite theoretical paper about Lie groups where all the definitions are from. Finally, a short shout out to Michael Goertz for providing both documenter interlinks and documenter citations to link from Lie groups documentation to Manifolds documentation, and to cite your sources with a nice bib file. If you want to see the slides again, they're on my homepage or with this QR code. So there's that. Thank you for your attention.
Time for at least one question, maybe two.
Awesome. Thanks for your talk. So I'm really curious, how tied is, I guess, Lie groups and I mean, this might be true of the whole manifolds ecosystem in general, to matrix representations? I work on a package that kind of can work with some of these kinds of concepts without referring to matrices through Clifford algebras. So I'm like interested in how, like, whether that can be worked with differently, or if there are different approaches that can be used.
Yeah, our functions are never typed. So the point G and the X are never typed unless you want to definitely distinguish between different representations. So for the SE3, we have 3 representations as a full homogeneous matrix, and as an array partition, then it's only 2. But then we type to distinguish those 2, that we know we are on this manifold in that representation. But as long as you come along with your favorite type on any manifold, you have to implement a few functions, and there you go.
Okay, cool.
And I hope we also always document kind of like, this function is API of Lie groups.jl to work with Lie groups, but it has the following default, so it's enough if you implement the following adjoint or something.
Awesome, thank you.
So we are completely not bound to matrices. If you come along with your favorite type, that's on purpose. Also for manifolds.jl, so even there we have we don't depend on a certain type. It's hopefully all untyped as far as we were able to do that. That should make it flexible, I hope.
Awesome, that's great, thank you.
Thanks again, Ronnie. Next up, we have Toby Driscoll with rational function approximation in Julia. Please welcome Toby. Thank you.
It's even harder to type, actually. So, good morning. I wanted to just start off giving you a few context tokens about myself. So I am an academic little brother of Alan Edelman, one of the Julia founders. And our advisor, Nick Trefethen, loves to brag that he was literally MATLAB customer #1. And he has the framed receipt to prove it. So we were both immersed in MATLAB from the very start of our training. To the point where, when I was still a graduate student, in 1995, I went to a MATLAB conference. And by an incredible coincidence, I ended up playing a game of MATLAB Jeopardy and excelling at it, doing really well at it, and got a job interview because of it. I went ahead and then wrote a lot of books using MATLAB and packages using MATLAB and things about MATLAB. The first version of Julia I downloaded was 0.3, and I played around with it. And I said, well, this is cute, but now it's time to get back to work. But I kept downloading new versions when they would come out. Sometime around version 1.3 or 1.4, I experienced an inflection point where suddenly I preferred working with Julia over MATLAB. And so now, 30 years removed from playing MATLAB Jeopardy, here I am at a Julia conference, so I'm very pleased to be here. Now, why did I write a package on rational function interpolation? So the approximation of functions is a foundational part of scientific computing. And one of the most common settings for that is interpolation, right? So I have some values at a finite collection of nodes, and I want to find a function that goes through those nodes. Of course, there's a lot of different ways you could do that, right? So the question becomes, how do you choose how to do this? And accordingly, if you do a very cursory search for packages, or for interpolation on Julia packages, you get a long list. You have to screen out some things about string interpolation, but this is just a very subjective subset of what comes up. So why add to this, right? So let me give you an example of two functions, tangent and the inverse tangent. So if you look at them from the interval -1 to 1, they both look pretty nice, right? In fact, they're analytic on those intervals. But we know that if you extend the tangent function out a little ways, then you're going to encounter a singularity, right? So you should not be surprised to find that that singularity could influence the convergence rate of something like a polynomial approximation, because polynomials don't have singularities. So that's an argument for using a rational function instead, because rational functions can have singularities, poles in particular. Now with arctangent, you can extend that as far as you want. It's still analytic, so that seems like a different situation. But that's wrong, because the right way of looking at these things is in the complex plane. So in these plots, the original interpolation interval from -1 to 1 is the black line. And you can see that we have a pole over here, because if you look at red, green, blue, it's going clockwise around that point, right? The 0 here in the middle, if you go red, green, blue, is counterclockwise, so you know that's a 0 instead. So the coloring here, the hue is the phase of the complex number on a cyclical color map, and the lightness cycles from dark to light for each power of E. So there we see the poles that we already knew about just by going in the real direction. But now we see that arctangent is really not that different, because it has branch points out at plus or minus I. In fact, you could argue that these are worse, because as you can see, right, the function is going to have a jump across the branch cut. And so this is another case where polynomials are going to feel the effect of those singularities, particularly as they become closer and closer to the interval. So let me back that up with some computations. So I'll say more about what's going on here later, but let's say I come up with a bunch of 500 test points from -1 to 1 on the interval, and then I define a function here that I'm going to use after the fact to check the error in the approximation. So here's the tangent from -1 to 1, and we see the singularities hanging out outside. So this is from the rational interpolation package, the function approximate. So I'm approximating f at that collection of points. And what comes out is a degree 8 approximation, right? So degree 8 upstairs and degree 8 downstairs. So that would be 9 plus 9 equals 18. But then there's a redundancy, because you can divide through by one coefficient. So there's only 17 coefficients there. Here I've got a polynomial interpolant from the approxfun package, and it uses degree 36, so 37 coefficients. Okay, so degree 8 plus 8, 8 and 36. Now if I change the scaling in x, I can move those poles closer to the approximation interval, the rational interpolant wasn't affected. It's still degree 8, 8, because that's just a pole sitting there. Chebyshev interpolant went up to degree 74. And I can keep playing this game, so if I move them a little closer, okay, now it feels those a little bit more. It had to go up to 10, 10, but the polynomial interpolant had to go up to degree 128. And so we can be a lot more efficient with a rational function in this case. Looking at the arctangent function. Now the singularities are on the imaginary axis. Degree 12, 12 versus degree 38. So 12 and 38. If I then move them 10 times closer. Now these are more genuine, more serious singularities, so more work is needed. So I went from 12 to 46, but the degree went up by a factor of almost 10 to 324. And if I go up another factor of 10, the degree of the rational went up just a little bit, and I got almost another factor of 10, so I'm degree 3,000 for the polynomial now. So that's a motivation for using rational functions as approximations. How's it done? Well, probably when I say the word rational function, this is the thing that you think of, ratio of two polynomials written in monomial form. The moment you conceive of these things this way, you've lost the game, okay? At least computationally speaking, you don't want to do that. There's a much better representation, which is the barycentric formula. So you can see that this too is a rational function if you just clear out the denominators, right? But it's one that's a much more stable and useful form. So I'll go into some more details about that on the next slide. There's another form, which is a continued fraction. And that also turns out to be computationally useful, which was discovered just last year. So I'll get into that a little bit later as well. There's another useful representation, which is a partial fraction expansion. That is in the package. It's not as well developed yet, and it's got some things I want to do with it in the future. So in the interest of time, I'm not mentioning that today. So let me start with this barycentric formula. It's designed so that if the zk's are my nodes, then the yk's are values at the nodes. Because imagine if z is extremely close to z1, right, then the only term that matters in the sums is k equals 1. And everything cancels out except for y1. So if I have a function I want to approximate, then what I should do is let yk be f at zk, because then r will interpolate it at those points. So the interpolation is just baked into this formula. Now these w's are called the weights. And for any value of the weights, I have this interpolation property. You may know, if you're familiar with the barycentric formula, there's a way to choose the weights so that this is actually the interpolating polynomial. That's actually a very simple derivation from the Lagrange interpolation formula. But I don't want to use the weights that way. I want to keep the interpolation and do something different. So instead of using them to get a polynomial, which can't have singularities, I want to use them to minimize the difference between r and f at a bunch of test points. If I try to solve that problem directly, it's pretty hard. It's very nonlinear. So what we do is linearize that problem instead by clearing out the denominator. And once you do that, you can repose this problem using linear algebra. This L here is known as a Loebner matrix. You notice that in the barycentric formula, everything is invariant with respect to a scaling of the weights. So I might as well let the weights have norm equal to 1. So I get this nice constraint problem. And now this constrained least squares problem is, in fact, finding the least significant singular vector of L. So that's the foundation of the AAA algorithm. You start with a set, let's say you have a set of n nodes and m test points. You can use an SVD to compute the weights. Now you have an interpolant that does a good job of approximation at the test points. You figure out what the residual actually is at the test points and choose the test point where it is the worst. And then you just greedily add that to your node set and repeat. So prior to the AAA algorithm, I don't think it's a controversial thing to say that computation with rational functions was a pretty niche idea, wasn't going anywhere. After the publication of AAA, things have gotten really interesting. And so there's a lot of applications emerging now from the ability, once people realize you actually can compute reasonably well with these things. Now, I could continue this example here even up to the arctangent of 1,000x. But if you're watching very carefully, you realize I'm conning you, right? So it says I've got an accuracy of 13 digits here with an approximation of degree 6969. And yet my test set, right, has a spacing of 2/500. Compare that to the fact that things are happening on a scale of 1/1000 here. Okay, there's no way that these test points, right, the test points are basically just seeing this almost as a discontinuous jump. Now, I could, let me expose that by changing my checking function here. So this does not affect the algorithm, it just affects the measurement of the error after the effect. And we see that this approximation is nonsense, it's not that good. Now, I could change the test points to have, this denser set, and it would do better. But then I'm resolving things everywhere, which is kind of silly, given that it's flat almost everywhere. It's long been known that you could have the nodes approach the singularity exponentially, and that would restore very efficient convergence. Of course, you'd have to know in advance where that singularity was. So to address this situation, last year I joined up with Yuji and Nick Trefethen to write a paper in which we described a continuum version of the AAA algorithm. Very simple. So if the blue dots are your nodes and the hash marks are your test points, let's say that happens to be the worst test point that you're going to add to the node set. So it becomes a node, and then you just subdivide in that neighborhood to get new test points. So by repeating this over and over, we can exponentially approach a singularity, and it discovers the singularities naturally. So that's part of the package as well. So instead of approximating on those test nodes, I can just approximate on the unit interval. Now, it's not getting the full 16 digits. There is a condition number here. It's kind of interesting. But now it's doing a reasonable job. With no greater degree, actually, it's doing 12 digits of accuracy compared to a degree 28,000 for a polynomial. And if we look at where the nodes are, we see that they are starting to get exponentially spaced near the origin where that singularity is. Okay, so I mentioned the continued fraction earlier. So this continued fraction idea has been known for a long time. Going back, I think it's about 100 years. I haven't actually found the original publication date, but a Danish polymath called Thiele showed that if you have this simple inverse divided difference iteration, then the continued fraction expansion that you see here, right, has these W numbers in it. If the W's are defined this way, then that continued fraction will interpolate and give you f of zk at each zk from 1 to n. So this kind of just sat around. It was known to a lot of people. And there was some work with it in the symbolic math community. But if you know anything about divided differences, they're numerically very unstable. Or the best that you can say about them is their stability is highly dependent on where the nodes are and the order in which you select them. And so people have rules for trying to figure out the best way to select them. They didn't, they worked okay in some circumstances. But then last year, Oliver Salazar-Celis showed that if you use the same greedy strategy, so you have a bunch of test points, choose the worst one and make that your next node, it really seems to stabilize this, this process. Now, he has arguments about it. I don't think they constitute a proof just yet of that stability. So I have a student looking into just how stable this is and a bunch of examples at least, so we can start to get our heads around it. But it's clearly working quite well. And what's really exciting about it is that this process here is just an order n iteration. So if I have n nodes and I want to add one, it's order n. If I want to build up to a set of n nodes, it's order n squared. AAA, each step is an SVD, which is essentially order n cubed, and to build up to n nodes is order n to the fourth. So I don't know a lot of n to the fourth algorithms that are in everyday use. Now, n is often quite small, and objectively it's fast. But the idea that we have a truly faster algorithm potentially is very exciting. So that's implemented as well, both in the discrete form and the continuum form. The continuum form is new as far as I know. So here again is arctangent of 100x. And so you can see timing comparisons seem to be getting a factor of speed up of a factor of about 8. So that was for degree around 45, I believe. So n is not that big, right? N's 45, and we're already seeing a nice speed up. So the potential is there maybe for doing a lot more than we could do before. Okay, so what does the package actually offer? So it's actually pretty small. The centerpiece is the notion of an abstract rational function, which has a bunch of definitions that are mostly just stubs to be implemented as an interface, essentially, of things that a rational function ought to be able to do or tell you. And then subtyped off of that is an abstract rational interpolant, which adds on the idea of having nodes and values at the nodes. So then there are types for barycentric form and for the TILA form that are subtyped off of there. So they're concrete implementations of these methods. You can construct those directly if you have a fixed set of nodes and values, or in the case of barycentric, you also have a set of test points that you want to specify. If you just want a one-off construction, you can do that. But to use these in an iterative fashion to build up a node set, you use this function approximate. So approximate requires two things from you. It requires data and a domain. The data, actually, I didn't put it here. The data can be offered as a function. It can also be a discrete set of values if you have a discrete domain. But think of it as a function. I want to then specify the domain as a vector of test points. That would be the discrete case. Or if I wanted to work in the continuum mode, you specify a complex curve or path or a region. That's done using a package called complex regions that I wrote a few years ago. And this thing returns an approximation. So the approximation has the original function so that you can do some diagnostics and the original domain, the rational interpolant that it found, a notion of what poles are allowed, and I'll say something about that in a second, and then some information about how it arrived at the rational interpolant. So my thinking here is that I want a package that is both useful just as a library. If you just want to construct these approximations and work with them, you can do that. I think it's pretty efficient. But also, the information is there if you want to study them, because these things are really new, especially the continued fraction case. And there's a lot of research yet to be done on how they work. So on this matter of allowed poles, here's an example of a function that has infinitely many poles in the unit disk, but it's analytic outside. So if I specify the domain as the unit disk, I am telling the system that I want an approximation that's analytic there. And basically it says, good luck. So the red dots here indicate the presence of a pole that's not allowed, because the only way of approximating this function is to put poles in there. The only approximation that was valid in the whole process was a constant. Okay, so that gold thing is the one that was returned. That's the only one that's safe. So that's not the way we probably should have done this problem, right? So instead, I want a function which is analytic in the exterior of the unit circle. And now it makes the same exact computation, but we view it differently. Now we like it, okay? Because that thing is analytic in the exterior of the unit circle. So my approximation can be as well. Now, it's only really discretizing the boundary of that domain, because this is complex analysis, right? If I don't care one way or the other, I could just say to allow everything. And now the dots are neither blue nor red, they're just black to indicate, I don't know, right? This is what you wanted. Let me just finish up with a few more fun little demos, things that you can do with regions in the complex plane. So here's an approximation to the zeta function in a rectangle in the complex plane. Just for fun, I used the Thiele method. So this is the world's worst Riemann hypothesis checker, okay? But it's fun to see, right? It's fun to see this function. And so if I look at the zeros of this approximation, they all have real part equal to 1/2. So I don't have anything exciting to announce on that front today. But it's fun. Here's an example of a disconnected domain. So let's say I want a function which is -1 on the yellow square and +1 on the blue circle. Now, I can't do this in continuum mode yet. I haven't thought about the right way to represent that structure. So I'm running this in discrete mode. But I go ahead and approximate that sine function. And these are the poles that you get as a result. So you get this nice boundary between them. Now, there's a little bit of a worry about these poles that are on the boundary of my region, right? However, if we take a closer look, so let's look for the ones that have a real part of -3, which is where that square is. So that's these two guys here. They have residues that are essentially 0. So this comes up a lot in rational approximation. They're known as Froissart doublets, right? You have a root in the denominator and one in the numerator that cancels it out. They're kind of an annoyance. They're an inefficiency, clearly. But for the most part, they don't do a lot of harm, as long as you're aware of them. And so here's the visualization of that function. So you can see it's nearly constant, not just on those two things, but in large areas of the complex plane as well. And if I evaluate R on the actual domain, then you see the values are all approximately either +1, right, or -1. So it was successful. Finally, here's a case of a function which is designed to have this branch cut in the right half plane, but it's analytic in the left half plane. So a lot of problems, you might want to have something happening in a half plane. So it's a little tricky to discretize the boundary of something infinite, like the imaginary axis. But it's child's play to transplant this problem to a finite domain. So this is also built into complex regions. So I can create a Mobius transformation that maps the unit circle to the imaginary axis. I don't particularly care which one, as long as it does that. And then I can compose the original function with that Mobius transformation. So now my problem is on the unit disk, but f is evaluated on its native domain. On the disk, then I get the branch cut sitting out here. Or if I wanted to then do this back in the original domain, I can compose with the inverse of the Mobius transformation, and now I'm back on the left half plane. Okay, so I'll leave the rest of the time for questions, and thank you, and just make a silent plug for my textbook. Okay.
Thank you, Toby. Any questions? One question here.
Hi, thanks for the talk. I was wondering, is it also possible to give derivative constraints at some node of the nodes?
So currently there is no way to specify derivative constraints. I've only recently added the ability to just compute derivatives of these objects. And there's something going on there. I'm not convinced that it's numerically stable in the vicinity of a node. So these formulas exist for the derivatives, but I don't know much about them yet. So I'm not close to offering that at this point.
Okay, thank you.
Quick question. You said that when they run this AAA algorithm, it scales like n to the 4th. has there been any attempts to like improve this, or is the speed like not really an issue? Like they're doing an SVD at every step, but they only need the minimum. You can imagine, okay, you do something like land shows, you restart, you keep track of the minimal things from the previous step, you carry it with you, you convert what you're doing your SVD of to something that probably has some hierarchical structure, maybe a little bit, and you can see that number going down.
It's even
quickly.
simpler because you can think of it as just an updating problem on the Loebner matrix. There are some SVD updating algorithms out there. I think it's been looked at a little bit, but there hasn't been a lot of motivation because, you know, when the thing is operating in 1/10 of a second already, unless you're doing 1 million of them, you probably don't care. So there hasn't been a lot of impetus to try it. I wouldn't be surprised if there's something faster, but I'm not sure you're going to get below n cubed if you do that. Maybe, but I'm not sure.
But there's hasn't been like any need yet. You
I don't think
haven't
there's been a
seen
systematic look that I'm
large-scale
aware of.
things where they really gotcha. Okay.
I have a question. Sometimes you use approximations in order to compute functions faster, and polynomials have this use multiply, which is very fast, but rational functions use divide, which is slow in a computer. So how does this this very beautiful method turn out with computation speed for the approximations?
Oh yeah, that's an interesting question. I haven't thought that much about the difference between a multiplication and division, but of course you're right. At some level, the division is much more difficult. Not only that, right, polynomials have the advantage, at least in Chebyshev form, you can use an FFT, right, which is a really big advantage. So the fact that you're having a degree 20,000 doesn't actually mean you can't use it, right, for a polynomial. So I'm not looking to say that, oh, you should immediately stop using approximand tomorrow and do this, but I think it's nice to be looking at this as an alternative in the future, particularly for problems where maybe you've got something evolutionary where often these singularities start to creep close to your interval or something like that. So yeah, it would be nice to avoid having to do it in a more expensive division, but that's beyond my pay grade, I think, at this point.
Thanks.
Thanks again, Toby.
Okay, thanks. Oops.
Next up, we have JuliaCon with non-abelian symmetries in the iTensor software library. Please welcome Julia.
Thank you. Thanks for having me today. So as mentioned, I will discuss about non-abelian symmetries in tensor networks and its implementation in the iTensor software library, which is a Julia library for tensor networks. So I will give a brief introduction to tensor networks, then some advertisement for the library that we developed at the Flatiron Institute in New York City. And then there will be a quite technical part about non-abelian implementation itself. And I will have a live demo, if everything went well, about how we actually use this in iTensor. So first, what is a tensor? It's a generalization of linear algebra to a larger number of axes. So when you have a vector, it's just an array with one axis. When you have a matrix, it's an object with two axes. And you can generalize it to higher dimensions. And from a mathematical perspective, it's a multilinear form. And once you specify a basis, you end up with a multidimensional array that you can store on your computer. So in tensor networks, we end up with many different axes. So we need a diagrammatic notation to represent all of this. So this is called the Penrose notation, where a tensor becomes a box. And all the indices of the tensor become just, the legs of the tensor become just edges. And I can generalize the matrix product when I'm summing over the indices as the tensor contraction where merged legs. So these are two vectors x and y, because I have one leg that I index with I, and when I share the leg, it means I'm summing over it. And now the output has no index left. So that's a scalar, which I can see clearly because there is no leg in my diagram. And I can write quite complex expressions like this. And I can easily see that the output is a matrix because it has two axes. Tensor network is a quite recent subject, but with many applications. It originally comes from quantum physics, so I will focus here in its use in quantum physics. I consider an object, for me it's a quantum wave function, and I represent it as a high-dimensional tensor. And this is way too big to store on my computer. Here I have 4 legs. Imagine that if I have a system of 20 particles, this will be 20 legs. And for 100 particles, that will be 100 legs. And it will scale as 2 to the power 100 coefficients. I cannot store it on my computer. So the point is, I will decompose this very large tensor into a bunch of much smaller tensors. And in doing this, I need to introduce these so-called virtual dimensions. And this is an approximation when the virtual dimension is small, but I can control the accuracy of my ansatz by setting the virtual dimension as big as I can. And for the physicists, this goes beyond mean field, because when I select the bond dimension with 1, the state I obtain is a product of scalars, so that's what you get in mean field. But I can get beyond this because I can carry entanglement in my system. So, as I said, it's a low-rank approximation of high-dimensional data with many applications. In quantum physics, this is extremely efficient because we know there is a link between the approximation I'm making, the accuracy of my ansatz, and which kind of quantum state I can represent. I have a faithful representation of any low-entangled state with a direct relation between the entanglement entropy of the quantum state I'm describing and the bond dimension in my system. And I can use many different ansatz. The most common one is so-called matrix product state, a so-called tensor trained by a mathematician, but there's also so-called PEPs or three-tensor networks, and even one more exotic. So, as you can see here, there are many, many legs, so you need a convenient way to deal with all these legs. And this is where iTensors comes in. So iTensor is a Julia library that is developed at the Flatiron Institute, and it allows to quickly build algorithms for tensor networks with large number of legs without digging too much into the details of how you define each of these objects. And it comes out of the box with many convenient algorithms so that you don't need to reinvent the wheel every time you want to write the tensor network algorithm. It's aiming for simplicity and high-level interface, such that it's accessible to non-experts in tensor networks. So how does it work? It relies on the concept of intelligent indices. Instead of constructing a tensor first, I first define the indices. Here, you see I have this tensor network that I want to contract, and I have 4 tensors inside it and 5 edges that are labeled by Greek letters. So first, I define the edges as iTensor indices. Each of them has a hidden unique identifier, which is hidden. Well, I can see it, but the point is I need now just to remember I have these edges. I construct the tensors from the indices I just defined. So the size of this tensor is the size of alpha, beta, and kappa, which is defined here. Here it's always 2, but of course it can be anything. And now if I want to write the contraction, I can just say X is the product of these tensors. And now iTensor will detect these tensors share indices, because I know these indices like alpha is shared between A and B. Therefore, I will contract A and B over their share index alpha. Then I will contract with C. iTensor will detect that beta is shared with the product of A and B. So it will contract this temporary object with C, and then the same with D. And I don't need to specify anything more because everything is stored inside the tensor and the intelligent indices, and there is an automatized way to detect which indices are shared. iTensor is now a quite vast ecosystem with many different libraries. So the flagship is iTensor.gl. It's just aiming to be the most generic possible. So just generic tensor network libraries with just tensor objects and indices objects and little else. Except that, yeah, you also have GPU support and you're able to support many different backends. We have our own backends that are either Julia arrays. It can also be GPU or more fancy objects. But the objective is you should be able to use any kind of tensor and wrap it inside the iTensor.gl. If you're a physicist, you may be interested into specific applications like DMRG or TBD. These are into the iTensor MPS library, which is just a matrix product state library using iTensor. A very fancy one is iTensor Networks, which is a very interesting library that can define tensor network and approximatively contract them on arbitrary graph. I think that's very fancy and quite useful. Finally, what I will focus on in this talk is the Fusion Tensors library, where we have implementation of non-abelian symmetries I will now explain. And just to say, this is a work in progress, so some of this, like iTensor MPS, you can use it right now out of the box. The non-abelian symmetries, you may need to wait a little bit more in order to, before being able to use it on your own. So, what I mean by non-abelian symmetries is associated with group theory, so it's a very broad subject. The point is, you have a vector space, whatever this is, and you know that you have a group that acts on it. So here you have an object that can be a two-element vector, but can be anything. And you have the concept of here a rotation, but it's an element of the group. And you know that under the effect of this element of the group, your object will transform in a well-defined way. You can define this even for wave function. Like if you have a 1D system, you can define the action of the translation on this system by just shifting every side by 1 unit. And this will be acting with a translation, that is an element of the group of translation, on your quantum wave function. This defines a so-called representation, meaning your Hilbert space of your wave function becomes a representation of the group. That's the mathematical name of this. And you can say that now, because of the group theory, your object will decompose as a sum of what we call irreducible representation. So it seems a bit abstract. Let's consider a matrix, a 3x3 matrix acting on a three-dimensional vector. I can decompose this matrix as its trace, plus the cross product of one vector that is defined univocally by the matrix, plus this object that is a traceless symmetric matrix. So this is just one decomposition as trace plus antisymmetric part plus symmetric part. The point is, under the effect of the 3D rotation group, SO3, all these objects behave in different ways. This object is a trace, it's invariant under the effect of a rotation. This object is a vector, so it behaves as a vector under the effect of a rotation. And this is what we call a spin 2 or tensor representation. All of these are different irreps, and my point here is my matrix that was a 9-dimensional object can be decomposed as a sum of 3-dimensional objects that are completely independent from the perspective of group theory. And these irreps have fusion rules, meaning if I take 2 spin 1/2, I can decompose the tensor product of the space made of the tensor product of 2 spin 1/2. I can show that it decomposes as 1 spin 0 and 1 spin 1. And you can check that the dimension match. Here you have 2 spins of dimension 2, because these are spin 1/2. So the dimension of this product space is 2 to the square, that is 4. And the dimension of the right is dimension of the spin 0, that is 1, and dimension of the spin 1, that is 3. So I have 4 equal 4 in terms of dimensions. In this talk, I will mostly focus on the group SU2, which is the most common group you will see in quantum mechanics, but it's the rest of the talk is generic to any compact Lie group. And I will use the fact that for SU2, I know the irreducible representations are what we call spins in quantum mechanics. And I will, instead of labeling them with half integer, as is the common way, I will label them by their dimension. So for me, 1 in bold letter, that's the dimension of the spin 0, and I will use it to represent the spin 0, knowing that it's both an irreducible representation and a vector space of dimension 1. Spin 1/2 is dimension 2, and spin s is dimension 2s plus 1. The first example I can mention is the s.s operator for 2 spin 1/2. So it's a 4-dimensional tensor. It has 16, meaning it has 4 legs, and it has 16 coefficients. However, I know this object lives in a can be decomposed as a sum of irreducible representation because I know that each of its legs correspond to a spin 1/2 representation. And I know I can rewrite this object as just the sum of 2 projectors, the projector of the singlet space and the projector of the triplet space. I have only 2 coefficients. More generally, for any quantum operator that acts on 2 spin 1/2 and outputs 2 spin 1/2, I can rewrite it as a function of only 2 parameters that here in this case I label as the eigenvalues of my operator. I want to only keep track of these 2 parameters in my whole tensor network computation. Instead of the 16 one, I can compress very efficiently my objects with only 2 parameters because thanks to group theory, I know that I can always recover all of these 16 coefficients from the 2 I'm storing. So and this is here an 8-time gain in terms of memory. It can go to up to thousands. Typically, you store only 1 coefficient out of 1,000 if you were not to use a symmetry. So that's a huge gain in terms of memory. The mathematical framework is, in order to implement non-abelian symmetries, I need to attach a group representation to any leg in my tensor network, which I was doing here by attaching a spin 1/2 to every leg. Now, I fuse the legs, and I say my tensor as a whole lives on the space that is the tensor product of all the representation of all of its legs. And the tensor is invariant, meaning I only allow singlets in the complete product. Therefore, if I have 4 spin 1/2, I can compute the product of tensor product of 4 spin 1/2 and decompose it as a sum of irreps. And SU2 fusion rules tell me I can make only 2 singlets, 2 spin 0, out of this. And I will only keep these 2 objects. These were the 2 coefficients I was keeping previously. This corresponds to the number of singlets I can make out of the legs. To handle this, I will need so-called Clebsch-Gordon tensor on fusion trees. So a Clebsch-Gordon tensor, we know Clebsch-Gordon coefficients are the way to fuse 2 irreps on 1 product irrep. So if I take 2 spin 1/2, I know I can make a spin 1 out of them. And there are rules that tell me that, for instance, the up coefficient, if I take the state up for the 2 spin 1/2, I obtain the state 1 for the spin 1. And if I want the state 0 of the spin 1, I need to take the state up, down, plus down, up over square root of 2. And all of this defines a tensor because I'm just constructing a dense tensor and filling it with Clebsch-Gordon coefficients. And now this is a tensor. I can compute a tensor network out of this and define a so-called fusion tree, which will fuse all of my irreps into 1 single irrep. And I can just construct this explicitly as a tensor network of Clebsch-Gordon coefficients. And it defines a basis for my tensor. I can use this fusion tensor to project the tensor I had on the singlet space. So I can define a projector on the singlet space as the sum of all fusion trees that will give me a singlet at the top. And this will define a singlet vector, which I obtain by applying my projector on the singlet space on my dense array. And I can go back and forth the dense form of my array and the symmetric form where I only store a 2-dimensional singlet vector. There is a difficulty here because there are different topologies possible for the fusion trees. So if I permute the leg of my tensor, I will implicitly also change the topology of my fusion trees. And this corresponds to a change in the basis of my coefficients. Therefore, when I change the topology, I have two different vectors, and the coefficients here and there are not the same. So I need to change basis. The way to do it is I know how to deal with the dense array. I know how to permute the legs of a dense array. So I can start with my symmetric state with only two coefficients, project it back to its dense form that is now has 16 coefficients, permute it, because I know how to permute a dense array, then apply a new projector made out of the new fusion trees. And I will get a new vector that still has two coefficients. But I can do better. This object is just what I obtained by intersecting everything but the coefficient of my old vector. And this is defined only by the group. This is independent of the coefficient I'm storing in my tensor. This object is the 2x2 unitary matrix that is only defined by the Clebsch-Gordon coefficient and the theory of the group. It has nothing to do with what is the data I'm holding in my old vector. So I can compute this unitary once for all, then it's set forever, because it's a pure mathematical constant. And I can reuse it over and over to compute the unitary and apply this unitary on my vector. I would just say that I need to conserve linear map properties, so I need to compute, let's say, singular values decomposition. So I will always conserve a form where I have two fusion trees, one for the domain and one for the codomain, meaning I'm metricizing my tensor. And it yields a block diagonal matrix that allows me to make efficiently tensor contraction as block matrix products. There is an optimization with 6G coefficients for the expert. I think I won't deal into this. I will now give you a clue about how we're implementing all of this in iTensor. So we are basing ourselves on the block arrays interface that define a nice block object that is here. It allows to define blocked arrays, any dimension. I will focus on block matrices that I can access with this object block. So it's a very nice interface for block matrices. It's very generic. We used it inside iTensor to define a block sparse array object that store dense blocks, but the blocks may be missing because it's a sparse array. So either a block is present and then it's stored as typically a dense array, although it should be generic, agnostic with respect to the type of the block, or there is the block is missing, and then you just don't store it at all. You just need to be careful when you take views of a block that may be missing, so you may need to initialize it first. We also need the concept of symmetries, so we need to store group representations and to store the space made of several irreducible representations. So we have so-called abstract sectors that encodes irreducible representations, and so-called graded unit range, that's an abstract unit range, that contains symmetry sectors. As this is spin 0, this is a space made of one spin 0 and two spin 1/2. I can define the tensor product of two spaces by computing directly with the nice Julia Unicode the tensor product of two axes, and this decomposes as a sum of irreducible representation as detailed by the fusion rule of SU2. And the nice thing about this interface is in quantum physics, we typically have several symmetries. If you know about the Hubbard model, you have one symmetry that consists in the number of particles. That's a conserved U1 quantum number. And one quantum number that's associated with the spin of your particle. And you can very easily define this object that is a Cartesian product of two symmetry sectors. It has both a number of particles and a spin. And I can define the tensor product of these objects in the same way as I was doing it before. Now, In Fusion Tensor, I will reuse a lot of the block sparse array. So I will store the axes of my tensor, including a bipartition that was corresponding to my domain and my codomain I mentioned before. A data matrix that's just a block matrix I mentioned before. And a mapping to deal with all my Fusion tree technology. And the point is, you should be able to use these objects without knowing much about the internal structure, but as if it were any tensor, except that now you need to have a bipartition of the axis. So let me show you how it works. So here, let's say I'm defining S.S operator for spin 1/2. So this is a 4x4 matrix. I can reshape it as a tensor with no 4-dimensional tensor with dimension 2 on every leg. I define the domain legs as a graded unit range with a spin 1/2 everywhere. I need to define also the domain and the codomain. There is a dual due to some arrow convention. I will gladly explain it in questions. And now I can compute a fusion tensor by converting my dense array into the symmetric format. And if I look at what I have now, I have a 4-dimensional tensor with 4 axes. And the information I'm storing are only the 2 coefficients I was mentioning before. So I had a 16 coefficient array initially in the asymmetric format. And now that I converted it to the symmetric form, I only store 2 coefficients. But if I compute the norm, and if I compute the norm of my dense array, I see that this is the same. So I'm conserving the norm. I have as much coefficient as before, even though I strongly reduce the amount of storage I had to carry. And I can also check that I have the same information as before. If I take my fusion tensor and convert it to an array, I check that I have the same array as I had before all this conversion. So there's no loss of information when going to 2 coefficients. And the last thing I would like to show you is I can permute my array. So now I need to permute my array and still specify a bipartition of the axis. I obtain another array. I can check that the norm of this array is the same as before. But if I check the data matrix, so the coefficient I'm storing, they are now completely different. Because I've changed the basis, I needed to change the coefficient I was storing. But there is still the same amount of information here, just the coefficients are expressed in a different basis because the basis I'm using depends on the bipartition of the axis. As a last comment, due to the symmetries and the fact I have way less coefficients as before, the contraction now becomes extremely fast. However, the bottleneck of the computation now is a permutation of the axes. So it means when you're writing a complicated tensor network algorithm, you now need to be careful about how you're designing the permutation within the tensor network, because this is now the bottleneck of your computation instead of the traditional tensor contraction matrix multiplication. And that's, as of now, that's not simple, and we're doing it by hand, which is a bit cumbersome, but it's still worth it in terms of performances. So to conclude, iTensor.gl is a very versatile tensor network library that aims to be fully generic, agnostic to any application you will want to use it for, even though it's originally coming from quantum physics. And the new feature we're developing right now is non-abelian symmetries, which offers tremendous gain in terms of both CPU and memory. And this will be available when it will be available. And I would like to thank Luca DeVos, who's around this week, Carl Spies, Matt Fishman, and my student Maya. And I thank you for your attention.
Questions?
Hello, Olivier. Thank you for your talk. I think you may already know what my question will be, but I heard down the grapevine that there's a package called TensorKit that already supports non-abelian symmetries. So what exactly do you think your implementation will reveal that maybe TensorKit doesn't do well, or what do you think you'll achieve new compared to what's already implemented?
High-level interface. Like, TensorKit is very powerful, but when you're a complete beginner and trying to read the documentation, as you may know, that comes with a few difficulties. The point is, in iTensor, you should be able to run DMRG without knowing anything about tensor network, basically. And you should be able just to say, I want to implement SU2, so just say implement SU2 equal true, and everything will fall down the box. And the point is to have a consistent ecosystem. Now, for the technical parts, we will probably have some interface with TensorKit, because the way we define, we compute the unitary only depends on your choice of Clebsch-Gordon. So we may call TensorKit as a backend in order to compute the unitary. But the objective is to have a very polished interface that's usable for people who are not expert on this. And all the technologies about fusion trees is designed to be hidden, such that basically only me knows about how it works. And you don't need to know anything about that to use it.
All right, thank you.
Other questions?
Well, since you mentioned that you are about to heavily refactor tensors, just wonder if you're going to put extra attention on using the new --stream option for Julia. That
The new, sorry?
There's a new way to compile Julia. We use the stream option, where it can automatically generate, well, it helps to generate a binary libraries or executables. And I'm asking this because we try to use iTensors, but it's not compatible with trim, and then we have to use other libraries. So I was wondering if you're going to put attention on that.
Okay, I don't know. I will be happy to discuss further.
Sure.
I don't know.
Okay, fair enough. Thank you.
Might have time for one more.
Any more questions?
Okay, yeah. We can thank the speaker again.
allow it in the at. You're picking up weird. Okay. Yeah, it may be.
So the weights were not normalized.
Yeah.
But what?
But it still follow the same distribution. So I'm like, I don't understand why simply normalizing the weights would change the behavior.
But what you're saying if it's ni dot ni,
Yeah.
when they're aligned.
W I J and I N J, and when they're aligned, it's one. When they're not aligned, it's
Excellent.
then I'm optimizing over.
Thanks, Alex.
So that's different. With energy.
You want to leave it this way, or do you
Doesn't
want to
have
take
a
this
mindset.
back out?
So when they're aligned, it's a hybrid.
Take this back out.
So
Oh, no,
if
I
try
have to leave this.
and
No change is good. Sorry, no change when it's
the
Okay,
no buzz.
still
values. I
would give me an
Oh,
optimization.
no, yeah, no, this is good.
Good.
I'm happy.
Now, in that case, if the weights
All right.
I can see how I didn't explain that.
then and
Oh my god, I didn't even see your question.
has a higher variability, then they would favor like more.
VGAN, you know it.
That's incredible. I love it. Very vintage, retro.
Normalization,
All right, well,
there's something that sounds like, not just like
All right, man, thank you again.
Don't, trying to understand what the consequences, so in certain states end up with outsized weight compared to other
We have
things,
another
because
one yet.
when things are normalized,
Your hand
each
is the
thing can
only
only
one
contribute up to one
I mean, that's the only one that
and
I
now
know
some
of,
things
but
just
I'm sure
contribute
there's more in
and
one of the.
what is that
I
priority?
don't have any, Mike needs some though.
I'm very low, and I need mine to put in this cable I just changed.
The problem is places where you have a bunch
You
of
need just a little
neighbors
bit?
are within,
Yeah, I can
are within that cutoff length scale that you can actually
Yep.
get to a neighbor. So, first of all, I don't even understand how the range is like so big, because
I mean, that's just on tagging, right?
so these are numbers these are on a per messaging basis.
So when I pulled,
Before, I mean, these are
journey,
based on the
looking
so
at you.
the number of neighbors can be changed as well.
You should have said anything.
Right, but it could be 18, but 4 is possible. Like how?
Number of neighbors?
Yeah.
Number of neighbors can.
This is
I was.
so in 3D
if we look at,
so in 3D with spheres you can have like 20 some with spheres.
These are the coordination numbers. So for different radii, different geometries. So we have 10 neighbors at like 0.1 for the discounting case. And similarly with like 1.45, but 7. This is just a radial cutoff. And I was typically running at 2.5 sigma, right? So at sigma plus 1, so 2.5 would be around 100 neighbors.
Okay. Okay.
Yeah. So
11.
100 neighbors.
So if you're teaching, yeah, I gave one to the people to like think.
Yeah, that's what the blanks look like.
Oh, the blank I gave, but not the
Oh, interesting.
Oh, two colors. Oh, you have two tags.
Yeah, I don't know why I got 2 tags. Yeah, there was organizer lunch or pizza. But you can just write out the analysis and see, does you can't say, oh, I had a method that did this great thing, but then I'll intentionally shoot myself in the foot, and then now it does worse. we had this issue where it wasn't clear why it was doing so well. You can't shoot it in the foot and then say, oh, well, now that causes it to do poorly. Rather, to understand why it was seemingly doing well, even when it shouldn't have.
This is here. Yeah. I thought this would be cool too.
A bunch of stuff was probably interesting. Yeah, there's a bunch of stat stuff in the middle. I just avoid the ones that seem very Julia specific, because a lot of people like these are about a Julia package, but I guarantee. One's at 3. I will be at that one for sure. And all. That might be interesting too. The one. It's kind of true at any conference, but here you know who the nuclei are. Yeah. Yeah. Yeah, that's what the volunteer training is in. Yeah.
And also, just to give you some context, just in the past few months, I've been trying to understand what squeeze slide is.
All right, so I think we're ready to get started with our afternoon session, and Hannah's going to talk to us about tagging, querying, and synchronization in quantum-savory.jl.
Sure. Okay. Hello, everyone. My name's Hannah, and I work for the NSF Center for Quantum Networks, working on Quantum Savory. There are a lot of interesting stuff about this software, but today I'll be talking about how it handles tagging, querying, and synchronization. So what is Quantum Savory? As some of the previous presentation touched on yesterday, Quantum Savory is a Julia package designed for simulating quantum communications and network protocols. For example, you can use it to model a range of scenarios, such as the one here, quantum repeater setup. So in this case, the goal is to generate high fidelity entanglement between the end nodes, which are the ones over there. We achieve this by first entangling the neighboring nodes and then performing entanglement swapping. And if multiple entanglements are established, we purify them. This entire process can be visualized, and we can also track metrics like the XX and ZZ correlators over time, as shown here. So the software is built with well-structured abstraction layer from low-level to high-level components. For low-level, as Andrew mentioned yesterday, you can plug in any backend simulator. Quantum Savory comes with Quantum Clifford for stabilizer formalism and quantum optics for state vector formalism. And above that, it includes a symbolic algebra layer that Andrew also talked about yesterday, and discrete event simulator, which is built with resumable functions and concurrent sim. At a higher level, we have state zoo, circuit zoo, and protocol zoo, which are collections of pre-built quantum components designed to support rapid prototyping of your protocols. But for today, the focus will be on the classical metadata tracker. So let's start with a simple protocol that entangles one slot on register A with one on register B. This is how the visualization looks in Quantum Savory. You can see that the register A has two slots, which are the dark gray boxes. And the first slot is already in use, indicated by the black diamond. So the first step in this protocol is to find an available slot on each register and to create the entanglement. So once you find a pair of free slots, you would like to entangle them. All right, that was very straightforward, but here's the thing. When you look at say slot 2 on register A, how can we know that it's entangled, what it's entangled to? What if we want to know the history of what it was entangled to before? Also, oftentimes we want to apply quantum error correction, which means that we need some sort of mechanism to send classical messages to relevant nodes. All of this can be tracked with a tag. So in Quantum Savory, a tag is an object that represents classical metadata, and it can also be queried. So you can create any generic tag using a descriptor along with associated ints or floats. For the entanglement protocol that I described earlier, we would have entanglement counterpart tag. This tag stores metadata about which node and slot a given qubit is entangled with. Okay, so now let's look at how entangler protocol in the protocol zoo handles finding a free slot. So here we have while loop, and that repeatedly checks for available slots on both node A and node B. If either of them returns nothing, then protocol waits for a fixed amount of time. Here it's 0.1 before trying it again. So in the diagram shown here, node A is full, so the loop continues waiting and rechecking until a slot becomes available, like here. Then once there is a free slot on both side A and B, we can break the while loop and entangle them. I guess entanglement part is not shown in the code here, but so this approach works, but it's not, as you can see, it can be not very efficient. So imagine the gaps are when the querying is being done, like the find free slot functions. And this orange bar here is when a slot becomes free. If the retry interval is too short, the first case, then the entanglement would happen shortly after the slot is freed. But the cost of doing this is pretty high because you're running lots of querying functions. On the other hand, if the retry interval is kind of too long, the second case over here, the entanglement would occur much later than necessary, and it'll cause some delay. Yeah, so ideally, instead of checking repeatedly, we want to wait for like an event and run the querying function then. So to do so, we implemented a new object called semaphore. This is like a custom structure that we built, which multiple processes can wait on simultaneously. So I'm not gonna go into details about how it works, but it uses the lock feature in concurrent sim. So once the resource becomes available, it releases, and in this like function called onTagChange, it'll like try to lock that feature. So once it's unlocked, all the processes that are waiting on it can go ahead and be processed. Yeah, so this onTagChange, which attempts to lock tag waiter semaphore on a register, that will be unlocked whenever there's a change in a tag. So this enables a process to pause and wait until a register tag is updated, rather than constantly polling for changes. However, there is a small caveat here with the current implementation. Yeah, so right now, polling is triggered by all changes on any slot for any tag for the register, which means that it doesn't precisely match that picture over there, because it'll trigger whenever a change would happen, but it might not be like, oh, this slot has been freed. It can be like, oh, this slot is actually entangled something else, but it'll trigger the loop. So to improve efficiency, we plan to extend this mechanism to allow processes to wait on changes for a specific tag, rather than reacting to all tag updates. As briefly mentioned earlier, tags can also be used as messages that are sent through either classical or quantum channels. Typically, we have a tracker running on each node or register that kind of like listens for those like tag-based messages and takes action based on their content. So for example, for the example I was like talking about, the entanglement protocol, there is a entanglement tracker that listens for tag like entanglement update X, entanglement update Z, and entanglement delete, and applies the corresponding correction. Or I guess for the deletion, it deletes the entanglement if needed. Yeah, so this is pretty important if you want to do error correction protocols. So let's go back to the example I was talking about. And here is the improved version that we pushed, where now we can wait on tag changes before we run find free slot functions. So if we don't specify retry lock time, then it waits for tag change on either node. Okay, so now we'll see how these metadata tracker and synchronization work in a full stack example. So here, what we're trying to do is a 2-to-1 purification or distillation, same thing. That is, we have those red two low fidelity, long range entanglements to begin with, and we want to purify them into an entanglement with a higher fidelity, the green one over here. So instead of using quantum gates, here we're going to be using a technique called measurement-based quantum computing, or MBQC for short. So this purification method using MBQC is based on a research paper by Scikit's group, which is part of Center for Quantum Networks. And I thought this is like a good, simple example that kind of like demonstrates how the classical control works in quantum savory. So yeah, so as I explained before, we start with two low fidelity entanglements. They're long range, so each of them are, like this is register A, this is register B. They're like far away from each other. Yeah, so like between them, they cannot communicate, like say faster than light. To do measurement-based purification, we do need extra qubits. So we need two extra on each side. So each register would have at least 4 slots. Yeah, then what we do is we entangle these qubits by creating a cluster state. Basically what we do is we initialize the yellow ancillary qubits with plus state and apply C-phase gate for the lines drawn over there. After that, we can measure these qubits and apply correction. So I'm not gonna get into details on like what basis we have to measure them and in what order and what kind of corrections we have to apply, because it's not like very relevant to what I want to talk about in this talk. But at the end, with some probability, we'll end up with a purified pair here. So let's go over this in terms of submodules, which are small components of the protocol, and also tags. Okay, so first we run entangler, which establishes the initial low fidelity entanglements between the red nodes over there. When it's successful, it'll tag the slots with entangler counterpart as before, I guess. At the same time, we also have this subprotocol called ancillary setup, which joins those extra qubits, basically creating the cluster or graph state. Once that is done, we mark it with setup ready tag. So once both of them are established, we finish creating the cluster state as shown. That's like being done during this like purify submodule. And we take the measurements on the top three qubits on each side and apply like the corrections. So once the measurements are done, we mark it with measurements done tag for both register. And so we're gonna have a measurement result for the second red qubit. And we're gonna send the result to the other register through the channel. And we have a tracker which receives the message and compares it with the measurement on the current node. If they match, then the purification process was successful. And we tag the green qubits with purified counterpart. And I guess like if it failed, the measurement results don't match, we kind of like scratch everything and start from the top until we get the successful process. So that was a high-level idea on how to do 2-to-1 purification work using measurement-based quantum computation, which shows how tracking works in quantum savory. Okay, lastly, I wanted to share a few ways you can get involved. I guess it was mentioned yesterday as well, but you're welcome to contribute to Quantum Savory. We are running this NSF-funded bug bounty program where you can earn a few $100s by helping us improve the package by implementing new features or fixing some bugs, whatnot. Yeah, so you can find more details on the bug bounty page linked here. And also, we just wrapped up the second Quantum Numerics summer school last week, and we'll probably having the third one next summer. So if you're interested in participating, you can find more information at qnumerics.com, but that'll be for next summer in a year. Okay, so to wrap up, here's a quick summary of what we covered today. I introduced the classical metadata framework in Quantum Savory, highlighting the tag system, checker synchronization, and weighting mechanism using semaphores. And we walked through a full stack example of 2-to-1 purification using measurement-based quantum computation, or MBQC, where we saw metadata tracking in action. And finally, we had a quick plug on how you can get involved by contributing to Quantum Savory through the bug bounty or by participating in the Quantum Numerics Summer School. Okay, well, thanks for your attention, and I'm happy to take any questions.
Awesome, thanks, Hannah. Questions from the audience?
Hey Anna, thanks for the nice talk. So I understand you set up a mechanism to wait for specific things to happen in your simulation, in the content network simulator. How hard would it be to implement something similar into the concurrent sim lower level discrete event simulator to wait on certain types of events, for example? Would that be transferable, or?
Sorry, can you repeat that?
So you're waiting on specific things to happen in the simulation, like a specific tag change, for example.
Yeah.
But I noticed in the concurrent sim simulator that this is built on top of, so such a feature doesn't really exist, which I guess is why you needed to build it. How hard would it be to take this feature and put it into the concurrent sim simulator, so that you can wait on specific event types, for example?
So if I understood that correctly, you want to use the concurrent sims, like the lock
So
feature?
for example, in
Yeah,
concurrent sim, it will be useful if you could sometimes say, like, I want this process to wait for something particular to happen in the simulation.
Right.
But the features for that are kind of limited, and I think that is in part why you had to like build this whole text system to wait for specific things to happen.
Yeah.
How hard would it be to like take this new feature and contribute it back to concurrent sim?
Honestly, like what we built was pretty general, so I think it can just like be integrated pretty easily. Yeah, like it was. I don't think there was anything specific to like say like quantum savory really. Yeah, that's a good suggestion.
That would be cool.
Mm-hmm.
Any other questions? I actually have a small one, which is just kind of like as someone who's trying to get a feel for how these systems are built and scale. Like when I think about like having lots and lots of sort of different networking systems that I need this concurrency problem to be solved for, like what are the kind of the key challenges to like simulating larger and larger systems in this kind of framework that like is everything as built? Like, does it seem like, okay, things should scale okay, or like there are going to be more challenges as larger and larger systems need to be simulated?
Personally, like the ones I've simulated, I like never ran into like a problem where I had to like wait for like a really long time. Like mostly because I didn't really get to work on like a very large system. Yeah, I am not sure.
Okay, yeah, well, maybe we can, talk more offline, because, that would be interesting to hear. Okay, well, if our audience is okay, I think we maybe can take a short break, let our next speaker set up, and 7 minutes or 5 minutes or so? Yeah, perfect. All right, let's thank Hannah again, and take a short break.
Not like spin systems, right? So it's more like quantum many bodies with like qubits. Sorry, I don't feel. Oh, sorry, I don't feel good. I think I'm sick. I'm really sorry. I think I will not make it.
Yeah, no problem. Yeah.
No, yeah. Yeah, sorry, I will stay seated and think, I think I can give the talk. So I'll present this method that I'm developing to do many-body simulation. So it's like spin, qubits, not continuous stuff, so discrete, based on this polystring approach. Yeah. So yeah, I'm developing this package called polystring.jl, so you can check this out. So the main motivation is, of course, we cannot build the whole Hilbert space because it's exponentially big. So then we need to take advantage of. Sorry, I don't see my slides on my computer. We need to take advantage. No, I need to take. Yeah. Okay. The thing is.
This is wireless.
Okay. Yeah, I'm just annoyed because my slides only shows there, but not on the computer. I don't know how to do it. No, it's fine.
We can do this, and if you want, I can flip your slides.
Okay. Oh. Okay.
Yeah.
So the strategy is to take advantage of locality, right? Because now if you have a system that has most systems of interest are local, right? For example, here some Ising system, interactions are in terms of these polystrings, right? The I plus 1, for example. So there is some local structure, and if you have a system that has this local structure, then all the dynamics will not explore the whole space, and so we can take advantage of the structure to have some, numerically, to have some more efficient representation, right? And I can. I will manage. Yeah, thank you. Okay. So if you have, for example, a local system that is gaped, then the ground state will have some area low, and in this case, for example, then tensor networks will be advantageous because there will be low entanglement in the system. But here, what I want to show is more there is not only entanglement. If you have something local, there is not only entanglement that is low, but there is also this notion of non-Cliffordness. So if you have a Clifford circuit, it's something that maps every polystring to a single polystring. And if you have something that is non-Clifford, then the polystring can be mapped to multiple polystrings. So there is also this notion of how complex the dynamics will be, on how the system will be to track if you look at this non-Cliffordness. Right? And the idea is, if you have low entanglement, there is this two way you could quantify how your quantum problem is hard, right? With entanglement and non-Cliffordness that we call magic also, right? If you have heard about this thing. So if you have low entanglement, then we expect tensor networks to be very efficient. And if you have zero non-stabilizerness, non-Cliffordness, then so if you have a Clifford circuit, then you can just simulate. It's just a stabilizer circuit, right? We can simulate this efficiently. And then the point is this polystring approach, so something a bit in between, I hope. So yeah. Okay, so let's first define what is this polystring, in case you don't know, just start from scratch. So any Hermitian operator can be represented as a sum of polystring. So these polystrings are tensor networks of polymatrices, and if the operator is Hermitian, then the coefficients are real. So here, for example, we have some operator that is defined on 3 qubits. And the first term is, we call it 3 local because there is 3 non-unit polys. The second term is 2 local because you see there is 2 non-unit polys, XX. The third term, 1 local. And we will refer to this as the length of the polystring. So if a polystring has length 4, for example, it means, I will say, it means that there is 4 non-unit polys in this string. So now the point is, if you have an operator that is in this form, you can actually store it as a dictionary where the keys are the polystrings and the coefficients are the values. The values are the coefficients, right? And this is what we do in this polystring package. So there are 2 main advantages of doing this. The first advantage is that we can like store this, represent this polystring actually in binary very efficiently, and then all the algebra in the polystring, all the poly algebra, can just be mapped to bit strings operation, so low level logic on the bit strings, and so this is super efficient because this is what like your computer is meant to do, right? It's just logic. And then the second advantage is that if once you have the operators represented in this form, then there is some natural way to truncate the operators, right? Because now you see if you have something that is non-Clifford, then the number of polystring will increase and explode during dynamics, for example, if you time evolve something. So you will need some strategy to keep the amount of string manageable. And in this representation, it's very natural to say, oh, if, for example, a string is very non-local, you would like to discard it, or if it has a small coefficient in front of it, or something like this. So let's look at this how we encode this binary encoding. So the idea is you can map the poly matrices to just 2 bits. And then if you want to represent a polystring, so for example, these 2 ones, you would read, for example, x is 0, 1, 0, 1, so 1 is 0, 0, 0, 0. So then each polystring is represented by 2 integers. And now if you want to multiply the 2 strings together, you can just do exclusive OR on the integers, and this gives you the answer. So now you can, here you see I just did exclusive OR bit by bit, and then I can read 1, 1 is y, 0, 0 is 1, 0, 1 is z. Right? This is up to a phase. There is also a phase, right? Because the product of 2 polystring is not commutative, right? And this phase we can also get it from some like logic, just some counting some bits. So you see that like, this is super cool, it's super efficient because now we just need to, it's like we have like a matrix-free way to represent operators on polystrings, and then we can just store these integers and do logic on these integers. So now that we have this representation, we can start like doing some operation, for example, multiplication. Right? It's like the most basic thing you will want to do. So then if you want to multiply 2 operators, yeah, operators will be described as linear combination of polystrings like this. And then if you want to multiply 2 operators, then you just loop over every polystring and multiply them 2 by 2. Right, so here V, this V is V and W are these 2 integers that store the polystring. So if I want to multiply A and B, I loop over every polystring, just like compute the exclusive OR, and then compute this phase. This phase, we can get it in this way. And then check if the polystring is in C, is in the product. If it is in the product, then we just increment the coefficient of the string. And if it's not in C, then we add it to the dictionary. And then I said, yeah, the other like point of this method, like other strategy that we really need is some way to truncate operators. Because if you want to just keep track of everything, and quickly becomes intractable. So there are multiple ways you could truncate. Like the one natural way will say, oh, I want to drop long polystrings, for example. Because if you would like to measure local observables, local observables are supported on short polystrings. So if you compute overlap between local observables and long polystring, it will be 0, right? So then you don't necessarily want to keep track of the very long polystrings. Or you could also drop strings with small coefficients. For example, if you have some distribution where only a few polystring matter, and you have a lot of polystring with very small coefficients. And what's very interesting is if you have noise, and in particularly depolarizing noise, then this noise will make long polystring decay. And like depolarizing noise will make the coefficient in front of long polystring decay exponentially faster in the length of the string. So then this is like a very efficient method to actually simulate a noisy systems. Because this has been like proven actually that you can simulate a noisy circuit in polynomial time if you have a little enough, like if you have noise, it can be a crazy polynomial, right? But and the way they prove this in this normal Yao paper, Yao group, is that after some time, the long polystring will decay exponentially with their length. Yeah. So let's take a look at this implementation. Here I show you some example where how to construct first operators in this polystring package. So in the left, so it's like if you have used the iTensor, it's kind of the same convention to construct MPOs, I guess, in iTensor. So for example, here I declare an operator on 4 qubits and then add the X on the first one. So this will be this string. Then add another string, for example, with Y. So this one, and add the coupling between the third and the fourth qubit, right? And yeah, and then you can do very large system from scratch, right? For example, here you can make an operator that is supported on 40 spins, right? Because you don't need to build any matrix, right? It's just one string. This is just one string. So the cost here is in how many strings there is in your operator. And here I have some example just for multiplication. Truncation. So for example, if you multiply, you see these two strings, these two operators A and B. They have both each 2 strings each, and then now the product now has 4 strings. It could have less, right? Because there could be multiple strings that multiply to the same, and then they become also less local. So these are 2 local, and now this is like what? This is 3 local, right? And so then if I want to truncate it, for example, you can just do truncate and then keep only the 2 local parts, and this will discard the 3 local parts. And there is a bunch of other methods to truncate operators in the package. Okay, so let's look at what we can do with this. So now that we have a way to store operators in this way and to do multiplication, then we can start to do some dynamics, right? Natural way to do this would just be to integrate time evolution equation. So the point is, I have not spoken about states. It's only Heisenberg picture, this thing. It's really, I have an operator, and then I will step by step compute a few commutators and time evolve my operator. And then during time evolution, add some noise. This noise will make the long string decay, and then discard the string with small coefficient, and this way you'll be able to keep the problem tractable. So yeah, here is like how I will do it, for example, for time evolving some Ising chain. So here you will build your Ising chain. by looping over each qubit on each interaction. It's kind of the same way you will build it in iTensors, right? If you know. And then let's say you want to compute, to time evolve some operator in the Heisenberg picture and compute this these correlators. Then what you will do, you will loop over each time step. Every time step, you can do a step from quota, for example, and then add some noise, and then trim, so only keep a certain amount of strings. Like, let's say you want to keep M string, and then you keep all the M string with the highest coefficient in front, and the noise will make like the long strings decay. Yeah. So yeah, I can show you some benchmarks, some examples I've done, some examples that are in the paper also. So we found that this is quite like efficient at exploring this hydrodynamics. You know, so if you have a chaotic system and you look at certain chaotic system have hydrodynamics property, right? If you look at this kind of correlator here for one spin, for example, then this will decay and diffuse in the whole system, right? And the way you will do this is you will see this is that this correlator in 1D will decrease as 1 over square root of t, which are these gray lines. And so we did some benchmark with these systems. I think this was XXZ with next nearest neighbors. And we really find that with the polystring method, we can do much longer times than with MPOs. So the MPOs method are in color, and the polystring is in black on the same machine on the same amount of time. And other way I mainly use this method is to study this Krylov space approach for like operator Krylov space. So here we like you build operator Krylov space for the Liouvillean by successively commuting some operator with Hamiltonian, and in this space you have some like cool properties because you can now time evolution is just a single particle in a 1D problem, like in this new space that you build by taking this successive commutator. And we can also explore like chaos and integrability in this space. And it happens that this method is actually very efficient at computing these commutators fast and like, yeah, much better than tensor networks actually. I guess I have 5 minutes, maybe. Yeah, so you can take a look at the documentation website. There is some example how to construct operators, how to time evolve them. Yeah, to make quantum circuits also. There is a front end for quantum circuits. This link shows. Yeah, also it's very efficient to represent translation invariant system in this representation, right? Because you don't need to store all the string on each side. You can just store the strings that are supported on, like that are centered on one side, and then have a rule to translate to generate the whole operator. Yeah, I have kind of a few slides to kind of summarize the idea. So ideas, you have some Hamiltonian, for example, some operator that you will construct in terms of polystrings. And now, let's say you want to time evolve some operator A that you represent as a sum of polystrings also. Then you will compute a few successive commutators, right? Like just time evolve step by step with H. And then your operator you are time evolving will become more and more complex each time you commute with H, right? Have more and more strings. So then if you add some noise, the noise will make the long string decay. So this one you see there are like 2 locals, 3 locals. Wait, yeah, the 3 local strings will decay faster than the 2 local strings in this example, for example. And then you will truncate, so remove the strings with a small coefficient in front of them. Yeah, I think that's the main idea. Yeah, things like the main advantage are this way we truncate the strings, and also the method is that geometry agnostic, right? There is no it's not about 1D or like you can do whatever graphs you want or whatever, just because everything is stored in this string representation, right? So I think this is like a main advantage compared to maybe what we can do with tensor networks. And it's quite stupid, I think. It's it's not clever at all. It's just yeah, you represent the operator as a combination of polystring, and then you do algebra. So I think there is room for a lot of improvement by making it clever. Particularly in the way we truncate the strings, I think. Maybe we can try to have a way to predict what will be the important strings, maybe based on some machine learning trick or something like this. And instead of just removing the long string and adding nodes or something like that. Yeah, on the main limit is we mostly do Heisenberg picture, and we need noise to keep the problem tractable. Yeah. Okay, thank you. Yeah, and I want to thank Lucas also, who is here, who made important contributions to the package, made it faster. Yeah.
I'm jealous you have like the best logo for quantum information science package. I'm curious, with the time evolution, on each time step you are creating new operators. How does that work with the data structure that's being used? Do you have like new allocations on each time step? So that's part of it. And also, how do you do the deduplication of, if you have from 2 different locations, you get the same new polystring during the time step. How do you ensure that they're keyed together and they're summed together?
Yeah, so the operators are stored as dictionaries, so this is here, like C, for example, is the new operator, so it's a dictionary, and you will just check if the new polystring is in the dictionary. If it's in the dictionary, then you just increment the coefficient in front of it by the new polystring you want to add. And if it's not in the dictionary, then you add it to the dictionary. I think, is this clear? Oh, yeah.
I think in lieu of time, let's thank the speaker again and let our next speaker set up.
Definitely blinked on my end. Should be showing up in a second. Where is those? Aha! Okay. There. And I'll just mirror this way.
All right, so let's welcome Katie to talk about quasar.jl.
Cool. Yeah, thanks again. So I'll just apologize in advance because this is talk 3 for me today. So if I say something incoherent, please just ask about it later. So I'm going to be talking right now about a parser I wrote entirely in Julia for OpenChasm 3. So I'll talk about what OpenChasm 3 is and why anybody should, I guess, be interested in this. Then talk about some specific design choices I made in the package, and then hopefully finish with some discussion of, I guess, how this could be integrated with other people's packages. So quickly, I just want to motivate sort of what we're talking about when we talk about quantum intermediate representations. So for people coming from a more CS background, you probably know or remember that an intermediate representation is part of the lowering pass. So anybody who went to State of Julia today, you probably heard a lot about Julia lowering. So for any like high-level language, we have to lower to what we call like an IR, an intermediate representation, as part of the compilation process, and then target very specific CPU opcodes to actually run the code on like my hardware here, which is an x86 64, or like if you have an ARM chip, or if you're on some ancient supercomputer and you have PowerPC. So the compilation process effectively takes like your high-level Julia code, let's say, lowers it to some LLVM IR, for example, and then further targets some specific CPU target. So for quantum computing, we want something similar. We want some intermediate representation that we can lower some like quantum circuit to. Ideally, that is maybe like a little bit informed about the kind of quantum hardware we want to run on. And then use that to very specifically target the device. So for example, like I could give Piccolo.jl some intermediate representation of like, here's some gates I want to run. And then they would come back and say like, okay, Catherine, you want to run, you know, C0 on this qubit, and this qubit, and here's our like very up-to-date calibrations of how we should do that. That's the dream. Unfortunately, or fortunately, depending on your point of view, there's multiple competing standards right now for what the low-level instruction set should look like. We haven't really like all aligned on a specific one, and there's some reasons for that. So I'll talk about 2 of the most common, which are OpenChasm and Quake. So Quake, which is going to go first because we're not going to talk about it again after this slide, is an open standard that's developed by a consortium, which includes NVIDIA and Microsoft. It also aims to support a wide variety of hardware targets, by which I mean like trapped ions, various superconducting systems, including like being geometry aware of the connections in the system, even things that don't yet support gates, like some neutral atom devices, and it's compatible with MLIR. So the idea is like the dream would be that you would be able to do like one auto differentiation pass through the entire compiled stack, including the IR, which would be pretty cool. And what we're going to focus more on today is OpenChasm, which has been around for a while. It's an open standard developed and maintained mostly by IBM, although of course there's like input from a variety of people. It also aims to support a variety of hardware targets and with some extensions, low-level pulse programming. So for, again, everybody who's in that quantum optimal control world, that's also supported, but it's not compatible with MLIR. OpenChasm is pretty widely supported, as is Quake, and so we might, you know, be in a position where somebody gives us an OpenChasm file and we want to read that in and be able to run it or simulate it on either like a classical simulator or some quantum hardware. So for that, you need a parser. But the challenge we face when developing these quantum IRs is that, of course, the quantum landscape is like very heterogeneous right now, and it's hard to figure out something that's both broad enough to cover all of the different hardware types and different native gate sets that all of them support. So for example, if you want to run something on like IonQ's trapped ion system, you need support for the Molnar-Sorensen gate. It would be a little silly to not support that for trapped ions. But then for the superconducting qubit system, it doesn't really make sense to support an all-to-all MS gate because that operation isn't natively supported. You'd have to decompile it into some like large collection of C-naughts and swaps and all that bad stuff. So we need to support all the different native gates that are available on all the different hardware platforms if we want our standard to become widely adopted. And we even need to support, as OpenChasm and Quake now do, pulses in case the platform we're working with doesn't support gates at all, like if it's only analog quantum computing, or if we want to encode our own low-level gate calibrations for the device. So in effect, we're trying to like come up with the library of Babel, or Babel. See, I even can't agree with myself on how to pronounce it, across a variety of different hardware standards that are very aggressively evolving as we go. And partly also the problem we have is that nobody really knows yet what like the sort of the final evolution of quantum programming is going to be like. Like, of course, now, in retrospect, people are aware of things like the C programming language and Python, and these are like well-adopted standards that can lower to a specific LLVM-IR that is basically supported by everybody. But that took a very long time to reach that standard, and still not every single CPU out there supports it. So we're kind of in the quantum world in the position of trying to develop x86 64 or ARM 64, but it's 1952. So maybe if you were a very smart person in 1952, you could have foreseen what the low-level IR for classical computing should have looked like, 50 years in the future, but it would have been very hard to do. And we're also in the odd position of wanting to support like what's effectively the low-level opcode and then also the higher-level construct that lowers to it. So TLDRs, it's a hard problem. So I'll just go through some of the features OpenChasm has that has made it attractive to people. Why is this supported on a variety of different hardwares? One thing that's quite nice is you can define custom gates in terms of other gates and also add modifiers to them. So like here's a nice example on the right of a custom gate definition where you can compute the inverse of a square root of a Z gate that's targeting qubit A here, and A is just some arbitrary label. So this is effectively like a function definition sort of that I can apply this gate to various qubits A, and if I've defined a custom calibration for Z, then that'll be carried forward through this new gate definition, which is kind of cool. We support things also like qubit arrays, so I can define 2 arrays of qubits, like Q1 and Q2, and then I can even concatenate them. So then I can address things in the larger array of just Q, which now has 7 elements. And this allows us to define algorithms on the various qubits and then let the actual hardware vendor, when they run the actual quantum program, actually decide about the mapping or the embedding of the specific qubit array to their hardware. So this is a very active area of research, especially for the superconducting qubits guys, because they have, of course, non-all-to-all connectivity. But it's also useful just like for expressivity reasons. We also have some, to me, weird indexing behavior. So you can define integer or float types with basically like an arbitrary number of bits, and then you can just bit index into them. This is like kind of annoying for doing like truth checks, or I mean, it's kind of useful for that, but it's kind of annoying from the trying to like parse some of this code point of view. And there's a lot of sort of maybe odd semantics if you're coming from the Julia world that OpenChasm supports. You can splat across qubit arguments. So to give you a sense of what that means, if I have 4 qubits in this array Q1 and 1 qubit in Q2, if I write CX Q1 Q2, this will be applied 4 times across each element of Q1. Which is, again, non-intuitive, and I can see some of the HPC people in the back are not happy about this idea. So there's also a bit of an interesting combination of sort of like Pythonic and then C-like semantics. When I spoke to the IBM folks who are on the OpenChasm steering committee, they were like, a lot of people find that OpenChasm is very C-like because there's braces and semicolons, which is, I'm sure many other languages would be interested to hear that like C invented those constructs. But that kind of like function and gate definition semantics is somewhat C-like, and then some of the list comprehension is more Pythonic. And recently, they've had an upgrade from OpenChasm 2 to OpenChasm 3 that supports more advanced programming features like control flow. So you can do if and else on the result of a measurement. If you want to do like mid-circuit measurement for quantum error correction, you can write loops, which is very important because it can dramatically shorten the length of the program. It's pretty important if your program is like going from 500 kilobytes to just 5 for how quickly you can parse it and run it on the actual quantum hardware. It supports dynamic circuits, as I mentioned, defining functions. So like we're getting closer and closer to like something that's actually a more Turing-complete language. And there's also a nice standard library of gates that are built on top of the very bare bones 3-argument U and G phase, which is enough actually to have a Turing-complete set of gates on the hardware. But you can build up more complex ones if you want, like C0, X, all of our buddies. Okay, so here's just a quick example of what a full OpenChasm script might actually look like if you haven't seen it. This implements integer addition using qubits. It's maybe like kind of a goofy operation to do on qubits, but oh well. So you can see how you can define some gates, majority and the unmajority, define some qubits for actually like doing the operations. And then I'll kind of just breeze through here. And then you define an output register, which is a classical bit. That's why it's called bit. We initialize the qubits by doing a reset on all of them, and then start doing some classical control flow on the actual qubit results. So here we can see that we're applying the X gate on the ith qubit of qubit array A if and only if one of the bit of the input integer is 1. And you can see maybe why also people describe this as a little bit of a C-like semantic, because it's kind of hard to read. So for humans, this is a bit frustrating, and we usually don't write the OpenChasm3 directly by hand, but it's a little more expressive than OpenChasm2, where you would have had to hand unroll this loop, which kind of sucks. And then finally, we do a few more operations and then measure the outputs to the classical arrays, and we get the added result. Hooray. And you can also do like one-line for loops, which is really exciting. Everyone loves a one-line for loop. So these kinds of sort of OpenChasm scripts, love them or hate them, or just kind of not have a strong opinion about them, I guess, are very widely used in quantum computing and also simulation of quantum systems. Like if you want to, take this and say like, okay, I have this sort of noise profile for the device while the device is going through a calibration cycle. I'll simulate the execution of this circuit and figure out whether I can successfully add two integers. I probably won't be able to successfully add them, but maybe I can make progress on adding integers. Obviously a very complicated operation. So we need some way to kind of like take this sort of Chasm script and load it into the simulator or load it into the hardware. And that's where quasar.jl comes in. So this is a package I wrote for pure Julia parsing of Chasm. So with like a little bit fudging of the name, it stands for Quantum Assembly Language Parse R. Unfortunately, the English word parser ends with ER, but a quasar is an object that people know about from physics, so there you go. It's entirely in Julia, as I mentioned. There's an MIT license for it, and it supports nearly all of OpenChasm3 and some of OpenPulse. So if you're an OpenPulse expert who wants to be able to parse it to Julia objects, would be very interested to talk to you, because I have no idea what the output should look like. And one thing that's, I think, quite nice about the package is that it has relatively, we would say, like agnostic output. So you can take what Quasar gives you and then change the dialect a little bit to target your specific library. So like if you're using iTensor, you can write an output function that will translate the result of parsing specifically to the gates iTensor supports. Or if you're using Qiskit, although they have their own parser, so I don't know why you would use this. Or if you're using like Quantum Toolbox or something like that, you can take the result of the parsing and end up targeting a bunch of different output programs. It's available on GitHub, and I think the other thing that's kind of cool about it is that it's not a super long package. So it's about 2,000 lines of code to do this, excluding the test files. And it's actually very easy to write OpenChasm3 files that are more than 2,000 lines long, so I thought that was kind of cool. So why did we write this in Julia? Probably you don't all need to be sold on the Julia programming languages. One thing that I think is quite nice about using Julia for this is that we don't have to rely on large, you might say like heavyweight Python packages like Antler, which is probably the standard for parsing in Python, and it's actually what the OpenChasm3 spec was developed with in mind. Julia also has really nice tools that are quite lightweight for sort of parsing and lexing these domain-specific languages. We also have nice support for conditional code loading through package extensions, which should make it easy to end up targeting various output formats or like output custom structs, like for example, like for iTensor or quantum optics. And so we'll hopefully be able to write plugins for many different packages, all based on sort of the same parsing result. So how does this actually work? So under the hood, Quasar uses this package Otoma, which is from the Julia bio community for tokenization. So tokenization is where I go through the entire script and I say like, okay, like int is a kind of token, it's a type. The Greek symbol pi is a kind of token. It's an irrational number. So first, I break up the entire file into little chunks that say, like, this is an opening brace. This is a closing brace. This is a type. And then once all that tokenization is done, I walk through all the tokens and put them together using the language grammar that I know, and that allows me to generate the result of a parsing operation. And in fact, Otoma is actually being used in the Julia parser itself, I believe, so it's pretty well supported. And also, if I run into problems, I can bug Claire, who maintains it, along with some other people, and get pretty good answers about how to fix things. So that's always good. One disadvantage of it is that it operates on the byte level, which makes it really painful when using Unicode. And OpenChasm3 supports a huge amount of Unicode as valid identifiers. Like all uppercase check number or letters are valid identifiers in OpenChasm, which is awesome if you're like in Czechia and doing some sort of qubit programming. But it makes it really annoying to parse stuff because the space of Unicode characters that are supported keyboard is very large, and the only way to tell if a Unicode character is in the like uppercase letter category is to just do a giant dictionary lookup. You can't just tell from the bytes itself, which is more a complaint about Unicode, but it's interesting that OpenChasm 3 supports a huge number of valid identifiers. So the advantage is that we don't have to pull in all of Antler and a huge number of recursive rules that it supports. We can kind of outsource some of that to Automa and other Julia packages. The disadvantage is that we effectively have to re-implement the entire grammar by hand, which can be buggy. So how this works in practice, we go through the tokenization procedure. We say like, okay, like this is a type, this is a number, this is a semicolon, and then we walk through all of those generated tokens, keeping in mind the rules of OpenChasm that like an opening brace better have a paired closing brace of the same type. Also, like a curly brace has to be closed by a curly brace. A square brace has to be closed by a square brace. And from there, we generate an abstract syntax tree. And then the final step is walking through the abstract syntax tree in a very specific, like a package-specific way to generate the final list of instructions that targets whatever package it is we actually want to, like in this case, simulate some quantum program in. So for example, step 3 would require actually outputting the kind of operators that iTensor supports through like AutoMPO or something like that. So anybody who wants to use the package can use all of this or a subset depending on what they want to do. So if you know kind of the output format that you want to support for your package, you can just do steps 1 and 2 and re-implement parts of 3 as you need, while also using the parts that are very generic, like stepping through a for loop. Okay, so from the user's point of view, how this works, you import the package, Quasar. You have some string that's the chasm file. I have a really simple one here. You just parse this chasm. So this generates the abstract syntax tree here, which is just like a generic tree-shaped object. And then we visit all of the branches and leaves in the tree to generate a final output program, which in this case could be like a list of circuit operations and then a list of measurements or results that we want to calculate at the end. Okay. One thing that's also quite nice about the package is that you're able to supply sort of a dictionary builder that allows you to specify custom gate sets. So like if you're some stealth mode quantum hardware startup and you have a set of custom gates that you support, that's some odd combination of like Molmer-Sorensen and then PRX. I don't know, what are some other goofy gates that not everybody supports? GPI, GPI2. Then, you have some gate decomposition that is highly optimized for your hardware. Like if you have some very special way to implement like a double excitation, if you're doing quantum chemistry, then you can supply a function that gives a mapping of gate names and your very specific implementation. And then as the parsing process proceeds, all of those will just be substituted in. And you won't have to like redefine every single gate as you go, so that's kind of nice. And you can also overwrite some of the keys in the standard library. For example, if you have like a super special, better implementation of like controlled Y. And so a built-in gate is a named tuple with fields that describe the gate's name, the arguments it takes, the qubits it acts on, and any modifiers. And this allows you to really quickly construct the output structs that will go into the final simulation or like, I guess, quantum hardware control package you want to use using stuff like struct-types.jl. And I know there is a successor to struct-types coming out, so hopefully we'll be able to support that too. Okay. So here's an example of what this can look like. You can just define a built-in gate for phase shift. It has a name, phase shift. It takes an angle argument called lambda, and it acts on a single qubit A. And then in the name tuple, there's a little bit of a reprise of this information. So the gate's type is a phase shift. It takes an instruction argument called lambda, where this can be either a symbol, a floating point number, or an irrational, because of course you want to have special semantics for supporting things like, applying phase shift of pi. That's a pretty special operation. And you can say, what are the default targets of it? Does it have any control operations? And is there a default power modifier? So this can also be very helpful if you want to define some built-in gate that's like a specific, integer power of some other gate that you already know how to implement. And these modifiers are useful also if you're passing something into like a simulation software, and you can very efficiently simulate a large number of control operations. Okay. The other thing we might want to do is handle pragmas. So OpenChasm also has, depending on your point of view, a useful functionality where they say like, okay, like we don't know all of the sort of instructions that somebody might want to apply because quantum computing is like still very new. So if you have some custom result that is implementable only on your hardware, like some sort of parity check, for example, then you can create a new instruction through Pragma that calls the parity check operator. And we have functionality in Kaiser that allows you to say like, okay, if I hit a pragma, I'll just call out to whatever function the user provides that knows how to step through that pragma. And it's up to you, the user, to teach the package the semantics and step through all the tokens in your pragma. And so you can set these at package initialization, and then when you step through the actual CHASM file, your custom parser and visitor will be called as appropriate. So one kind of annoying downside is if you had like a lot of custom pragmas, you'd have to have some logic to handle that within the single pragma parser. So right now we only support supplying one parser and visitor function each, but maybe you shouldn't have a lot of pragmas. It's up to you, I guess, or have some nice way of identifying them. For example, a use case where this might be helpful is if you're trying to do simulations and you want to apply noise operators. That's not at all supported in base OpenCHASM. So you'll have to define a bunch of pragmas for like your different cross operators that can occur on your device. And then you run the parser, and it loads in those cross operators and can then simulate the device using the noise model that you gave it. Cool. So there are some gotchas in the package. So currently, the visiting, so stepping through the AST happens all in one go. So expressing mid-circuit measurement is not yet very well supported. This is a super obvious to do for supporting dynamic circuits in general, and it's probably one of my top priorities for the package when I get back to working on it. Another very obvious one, partly due to my inexperience with OpenPulse, is not having a particularly good output format or output like representation of the OpenPulse operations. So again, if anybody here is coming from like a more quantum optimal control background, and they want to help me figure out what the output of the waveform and frame and all that business should look like, that would be awesome to have actual expert advice on how to do this. We also don't yet support annotations. That should be relatively easy to add. Another nice to have is modular arithmetic for the angle types. So OpenCHASM has a special floating point type that spans 0 to 2 pi. And then if you start going over 2 pi, it'll take the mod with respect to 2 pi. Julia does have an operation for this. It's called very creatively mod 2 pi. But the reason they do this is so that you can be guaranteed that the angle obeys the correct sort of like angular arithmetic you want, and that you're not having some like huge, massive float angle that's like overflowing what the actual hardware can represent. And in general, it would be great to support more dynamic circuits. I mean, for stuff like doing quantum error control, or even like error mitigation, we need dynamic circuits, conditional measurements, and conditional execution. So this is coming. I just need to have time to get back to the package. So I think this also like kind of taught me something about OpenCHASM itself, which is that the spec is very Python inflected. So if you like the way Python lists work, then I guess it's great. And if you like the way Python defines functions, I guess it's great. The main difference is that now functions have braces. But a lot of the operations and the way they work on qubits is kind of counterintuitive. A lot of the documentation examples in OpenCHASM just don't work, which is kind of surprising. And as I mentioned earlier, there's a lot of Unicode characters that you can support. And I would be interested in hearing like why it is that there's so many uppercase letters that I can use as an identifier when I think almost everybody uses either just ASCII or the Greek ones. It's annoying for byte-based tokenization, which again, maybe the answer to that is just don't tokenize by bytes, but oh well. I also just want to mention that things could be a lot worse. Like, although I have complaints about OpenCHASM, if you're parsing something like COBOL, which has been in the news recently because it's what the US government uses behind the scenes, you could be encountering a situation like this, where this person on Stack Overflow produces COBOL parsers and lexers. And the lexer, which handles 7-fold dialects of COBOL, has 22,000 lines of regex definitions. So although I have my complaints with OpenCHASM 3, I will say there's a lot worse that we could be dealing with out there. And overall, I think it's a pretty good spec for programming quantum hardware. So I'll just end, since we're near the end of the talk, with the roadmap. If anybody has any suggestions of what they would like, or maybe they just don't care about OpenCHASM parsing at all, which is also a valid opinion, just let me know. And with that, maybe we can do a question or two.
Questions from the audience?
Oh, Stefan has one.
What's the blessed procedure for adding converters to these other packages? Like, do you expect package extensions? Who's depending on who?
I think package extensions would probably be the easiest way to do it. Although it's an open question of like where the package extension should live, like who should own it? Should it be this or should it be that package? And I'm kind of agnostic on the issue. So if someone wants to add support for it in this their package, like maybe we can hash that out while we're not on stream. But I think it could make sense to just have it as an extension to this. And then, like, let's say we add an extension for, like, iTensor. Then, of course, yeah, if just iTensor and this thing are loaded, then we can output to iTensor. And if not, like, too bad, so sad. I don't think there's, like, too much problem with having, like, 10 extensions for a package. If the package.jl itself blows up for that, like, that seems like a big regression, so. Other questions? I have, like, no idea what time it is, so. Yeah. Who's next? If the next speaker is here, do you want to come up and start setting up?
Yeah, this is super cool. Would love to talk more about this. How does this play with the stuff that Unitary Fund is working on? UCC, I think it is. They have like open chasm kind of compiler, and kind of curious how this might play in with these kind of optimized compilers?
The short answer is it doesn't yet, but it's kind of an obvious target. So one thing you can do, for example, would be like to parse in the open chasm, and then with the agnostic qubit arrays, like when this gets compiled down, there's the concatenation. When this actually gets compiled down to what's run on the hardware, the compiler has to make a choice about which specific hardware qubits to target, right? Which is like usually informed by A, like the fidelities, B, the calibrations, and like C, the geometry. Okay, great. So then there's like an obvious use case to allow this thing to like plug into ZX calculus or whatever it is, or like UCC, and just like let her rip and see how it goes. But I haven't tried that yet, so that seems like it would be cool. And with that, I will hand it over to Hoos.
Awesome. Thanks, Katie. All right, so let's welcome Hoos to talk about optimization of quantum repeater networks using stochastic automatic differentiation. So take it away.
Thanks, Andy. Hi, everyone. I'm Guus. I'm a postdoc in Stefan's lab in UMass Amherst, and I'm talking about a paper that we wrote pretty recently, and it involves a bunch of Julia, so I'm going to highlight that a little bit in this talk also. It's titled Optimization of Quantum Repeater Networks using Stochastic Automatic Differentiation. I have some very basic slides about what a quantum network is. Let me know if it's too easy. But I imagine a quantum network as some kind of abstract service that is offered by some cloud. I don't know what it is like. But it's connecting a couple of end nodes, which are these blue squares. And it offers this service where it can make entangled states between these remote end nodes. Turns out this is kind of difficult if you want to go too far. I like to picture it a little bit as like you have a nice China plate collection and you're moving to a new house. You can imagine that you decide to throw them all these China plates like frisbees to some friend at the other house, and they catch them and then put them into the new cupboard. And that works kind of well if you're just moving across the street, but then if you're moving a little bit further, then most of your plates are probably not going to make it. Well, of course you can call more friends, put them in between, have them catch your plates, and then turn around and and throw the plate again to the next person in line. And if you make a long enough line, in principle, you should be able to cross a pretty decent distance without losing too many of your plates. And that's kind of what a quantum repeater is in a quantum network. What it would look like in a bit more concretely in an actual quantum network is that there's a line of nodes like this that we call a quantum repeater chain, where these quantum repeaters are the intermediate nodes. Every pair of nodes that is linked by a connection can perform some operation that creates entanglement between them by exchanging photons. And then at the quantum repeater, once it has entanglement established with both its left-hand neighbor and its right-hand neighbor, it can perform a measurement that is called entanglement swapping, that creates an entangled state between its two neighbors. And if you perform this operation on every quantum repeater in the chain, you're going to end up with entanglement between the end nodes. So I like to study quantum repeaters and quantum repeater chains using Monte Carlo simulations. And what we're doing here is that we have some simulation in the computer, and we're going to run the simulation to get samples of what happens in the network. We basically simulate a trajectory of how the history of the network for one entanglement generation could look like. And now these samples, we can use them to determine how good this network would actually be if we would like to do something useful with the network. For example, maybe we want to do quantum key distribution. We can simulate the entanglement generation. We can simulate measuring the entangled states and use this to determine how quickly we can make a secret key so we can communicate secretly using quantum key distribution. But now something else I would be interested in using these simulations is drawing samples again, but now not using these samples to say something about how good the network is, but say something about what the derivative of the quality of this network is with respect to the various parameters that go into the network. This is very helpful to answer questions like what hardware parameters in the network are actually the most crucial to get good performance, but also to decide for the tunable parameters in the network, which are the things that you can freely choose. They are maybe some knobs in the quantum repeater that say, how much do I do A, how much do I do B instead? How should we tune these knobs in order to get the best performance? And if we have derivatives, we can do gradient-based optimization, and that will make our life a lot easier. So to say a little bit about getting derivatives out of a Monte Carlo simulation, this can be a bit of an annoying problem. Let's say that first of all that we have some deterministic function that we can calculate with a computer. Then if we want to numerically determine the derivative, we can do this easy thing where we just say we calculate the function at point x, and we calculate the function at point x plus epsilon. We look at how much the function value changes over that interval, and then we just divide this epsilon by this delta. We look at the sort of the direction of this arrow that we can draw between the two data points, and that gives us the gradients. But now if we have a Monte Carlo simulation and we do the same thing, what we're going to get now is that there's going to be error bars on the data points that we have. So now we can do the same thing. We can just draw this arrow from one data point to the other and say, this is the gradient. Well, great. However, within confidence, this would also be a valid value for the gradients. But this would also be a valid value for the gradients. And you can imagine that the closer we push these two data points together without shrinking the error bars, sort of the more divergent these two arrows become, and the less certain we become about what the gradient is actually like. And to make this a little bit more formal, it actually turns out that if we take the limit of this epsilon to 0, then the variance of the estimate that we're going to get will blow up and go to infinity. So it becomes completely useless, basically. However, if we don't let epsilon go to 0, then we get a biased estimator, and the thing that we're calculating is not actually the derivative, but something that is maybe like the derivative. We're not really sure. So that kind of sucks. But the good news is that some really smart people at MIT, Gaurav Aya specifically, they came up with a method that they call stochastic derivatives that allow you to do automatic differentiation with stochastic discrete random functions. And the best part of this all is that they have a very nice implementation in Julia. And sort of the point of our paper is basically saying, hey guys, look at this Julia package, it's really nice, and actually this is super convenient if you want to simulate quantum networks. So basically most of the talk is just sort of showing a couple of use cases of how this can be useful. But because this is JuliaCon, I also want to say something about the software that we developed to actually do this. Usually I don't say too much about that, but I think it's useful and interesting. So the main package we developed in order to make to do the examples that I'm going to talk about later, is called quantum network recipes.jl, which sort of defines a language for defining quantum networks, and then also offers tools to evaluate these, sort of what is the quality of these networks that we have defined using this language. And of course, for us, the useful part here is that they have been written in such a way that it's compatible with the stochastic-ad.jl package, which is this package sitting underneath. So this is not something that we wrote at all. But this is a package that is very useful and a package that we really like to use, and a big part of our focus has been to ensure compatibility with that package. And then on top we also wrote another package that's called repeaterplacement.jl that offers some utility for talking about the location of repeater nodes in a network that is going to be useful for the second part of the talk also. In particular though, these two packages that we wrote, they have not been registered to the Julia registry. If anyone thinks that it would be useful to do so, let me know. I guess I haven't been able to decide whether it's useful for other people except for just me just yet. So if anyone has thoughts on that, let me know. So this package, quantum network recipes.jl, basically the main idea here is to sort of separate the network description from the methods that we use to analyze them. And what it looks like is that there's basically two important types of objects in that package, and those are the performance metrics, which is something like the secret key rate of quantum key distribution, the fidelity of the entanglement that we can make, the rate at which you can make entangled states, And then on the other end, there's network recipes, which are sort of, well, a full-blown recipe that completely describes how a network is configured, how it is defined, what it is running. It's sort of a combination of both the physical representations of the components that are operating in the network and the protocols that we're using to actually tie all these components together and make them be a network. And now, of course, because of Julia, we can actually set this up in a nice way where these performance metrics are just functions that are dispatching on the network recipe. So you can implement one method for each network recipe and in that way offer sort of a nice interface. So to give an example of that, let's look at a very simple example of placing a quantum repeater between two end nodes in a very small network. Let's say that the end nodes are separated by 100 kilometers and we can put the repeater anywhere in between these two end nodes on the line. However, there's a catch. On the left hand of the repeater nodes, there's losses in fiber that are 0.2 decibel per kilometer, which is kind of standard. But then on the right-hand side of the repeater, there's more losses. There's 1 decibel per kilometer. So a little bit an artificial example, but I just want to make it not too trivial and just throw some numbers in there. It doesn't matter too much. It's just an example. Well, let's say that we're interested in a performance metric that is the secret key rate of entanglement-based quantum key distribution in the form of the BB84 protocol. And as a network recipe, the thing that we're looking at, we want to say that there's a repeater that performs one entanglement swap to make entanglement between the end nodes. We use a depolarizing noise model, which means it's kind of white noise. All the nodes have a coherence time of their quantum memory of 20 seconds. And entanglement between any pair of nodes is generated with a fidelity of 0.95. Then if you want to put that into code, it's going to look something like that. We use the quantum network recipes package, and then we define a function that's just calculate the secret key rate of this network. We can define some constants. There's the distance of between the end nodes. There's attenuation on the left-hand side, attenuation coefficient of the right-hand side, the coherence time, the link fidelity. Then first we define the physical nodes of the networks using this node with memory, depolarizing memory with a specific coherence time. Then we wrap it up into a node recipe by using the simple node. This is sort of a trivial recipe that we call on this physical component. And then we do something similar for the edges, where we say physically the edges are a fiber segment with some attenuation. And in order to make this fiber into an actual recipe or some connection that can actually make entanglement, we wrap it around a direct transmission over fiber recipe. This means we're just sending photons through that fiber to the other side to make entanglements. Then we also define a protocol for the repeater, or for the repeater chain, which in this case is a swap as soon as possible without cutoff protocol. And finally, we wrap it all together into this chain recipe object, which takes the edge recipes, the node recipes, and the repeater chain protocol. Then we define also the method that we want to use for evaluating it, which in this case is some sampling method. It just means Monte Carlo. And finally, we can call this performance metric function, which is secret key rate BB84, on that chain recipe with the evaluation method. And then we can calculate things. And now the nice thing is that if you want to calculate derivatives for this, we can use this stochastic AD package to simply say, do the derivative estimate of this function at this function value. And that's super easy. So thank you, stochastic AD. And then we can just call things and calculate things. So to look a little bit more like this, if we look at this repeater between the two end nodes, and we look at the secret key rate and the UI axis here in this figure, and how this varies with the location, we see that we get this nice little skewed figure, and there's going to be an optimum somewhere around 80 kilometers. A nice way to find this optimum, of course, would be to actually use its derivatives. And to do that, we can use either the stochastic AD method, or we could use this very naive finite differences method, where we just calculate the 2 points and look at the difference between the data points. So let's see what the derivatives look like if we do that calculation. So here the blue points are the stochastic AD, and the orange points that are all over the place are this finite differences method. And we see indeed that the variance is really blowing up. Of course, with finite differences, it depends a little bit on how large it chooses epsilon that I was talking about. So this epsilon is pretty small, so we see that these data points are very close together and things are blowing up. We could also pick it a bit larger, but then while it starts to be a bit more nicer and smooth, it starts to become very biased and it looks very different now from the blue line, which is the stochastic AD. Of course, we can try to go a little bit in between these two epsilons, and then we get some kind of trade-off where it doesn't look too bad. But we kind of need prior knowledge about the function in order to decide what the good epsilon is in the first place, and still it doesn't look quite as nice as the stochastic AD result. So I would say that stochastic AD is actually blowing it out of the water right here. So great. And with that out of the way, we can actually look at some science and some results that we obtained using this. So one thing that I think this is very interesting and useful for is tuning rate fidelity trade-offs in quantum networks. So there's a particular type of entanglement generation that's very popular that's called single-click entanglement generation, where two photons send photons to some midpoints, and they do a measurement there, and if they detect one photon at the midpoint, they declare success and they have some entangled states. However, there's a trade-off between the success probability of that process and the fidelity of the states that you generate that is tuned by something that's called the Brightstate parameter that I call alpha here. And very schematically, like at the first order approximation, the success probability scales linear with alpha, while the fidelity scales with 1 minus this alpha. So basically, big alpha means a lot of entanglement, but it's very shitty, while a low alpha means we have to wait for a really long time, but once we get entanglement, it's going to be high fidelity. But what if we have some longer repeater chain and it looks very irregular like this, where the distances at the different sections of the repeater chain look very different? Then how are we going to choose the alphas such that we can run entanglements and make entanglement between the end nodes of this chain in such a way that the final entanglement that you produce allows us to get the most usefulness, the most utility. And where utility is defined according to some metric, and we're going to look again at the secret key rate of quantum key distribution because it's a very concrete number. Another question that we can ask is how sensitive is the performance of that chain with respect to the different parameters of the network. So specifically, we're going to look at the coherence times of these quantum repeater nodes and see how quickly things become worse if that quantum memory will become worse. So we're quickly going to look at a few results for that. So there's a figure here where we see the alphas for all these different links as they evolve while we're doing a gradient descent algorithm. So basically, they start all at the same value, which is sort of the optimal value if they would all be forced to be the same. But then we let the gradient descent algorithm evolve, and they all go to different values and go to different spots here on the map. And as we see, it's this blue line, which is the secret key rate of the total figure. It's going to go from approximately 1 hertz, which is not a lot, to 2 hertz, which is still not a lot. But well, that's quantum networks for you. So we basically doubled our secret key rate by doing a more complicated optimization problem. We went from 1 dimension to 5 dimensions. And that's great. And using stochastic AD, we basically solved this on my laptop in like a minute. So I would say that is pretty useful. And we can also look at the sensitivity of the performance with respect to these different coherence times, as I was talking about. And that's sort of shown in this figure, where the sensitivity, which is the derivative of the total performance, so the secret key rate, with respect to the coherence time at node n, where the n is also depicted on the x-axis, which has the weird unit of hertz per second. And we kind of see that depending on the type of protocol that we're running, we are looking both at a multi-shot protocol and a single-shot protocol. I won't talk about that too much, so I don't go into too much detail. We see that it can actually differ quite a bit per node, and it also depends quite a bit on what exact protocol we're executing. And this type of information could be quite useful because it tells us maybe something about how often we need to maintain the different nodes in the networks, because some of them might be quite critical, and so maybe we need to send a maintenance guy every month. While some of them are maybe not so critical, and we can send a maintenance guy every year. Or what if we have some money available and we can buy one new quantum repeater that is top of the line? Which of these nodes are we going to replace? Well, probably the one that has the highest sensitivity, because that would also mean that we could get the most improvement by giving it a better coherence time. So the second example I want to talk about, which is maybe a little bit more exciting, is repeater placements. And the problem that we can think of here is that there's some nodes in a network that we want to connect. Think of the first slide that I was showing, where there was this cloud that is a quantum network, and then there's some end nodes that we need to talk to each other. For example, they can be these okay, yeah, that's better. So there's these nodes in the network that we need to talk to each other to make entanglement between them. And now the question is kind of, if we can put quantum repeaters on this map anywhere, where would we be putting them in order to get some good performance out of that? So to make this problem a little bit more simple, let's look at a square where there's 4 end nodes. They sit in the vertices of the square, and we get n repeaters that we can put anywhere in the square, but we can only put exactly n. Then where do we put them? Well, this is something we can solve pretty nicely now with these simulations and with this stochastic AD. Basically, we can run some Monte Carlo simulations and use the stochastic derivatives to do a stochastic gradient descent algorithm on the locations of the repeaters. However, we can get stuck in local minima quite easily, so we use techniques from simulated annealing, where we start with a high temperature, where we make huge jumps in the gradient direction every time when we displace things in order to explore the parameter space effectively. But then as we cool down and the temperature becomes lower, we steadily close in on the local optimum as these steps become smaller. And this looks kind of fun. It's like there's these hot particles in the box that are jumping around. But then as the temperature becomes lower, they start to move more slowly. And slowly we can see that they're starting to settle in some kind of structure that maybe makes a bit more sense. Look at that. Beautiful. So if we do this for different values of n, we get a little bit of a zoo for solutions, like what are the optimal solutions depending on how many repeaters we like to have. So there's for 4, 5, 6, and 7 repeaters depicted here. And something that we might notice right away is that there's some kind of spontaneous symmetry breaking going on. Because we start with a problem that has the symmetry of the square. So that's reflection symmetry and 90-degree rotation symmetry. But now the solutions that we get do not have that. For example, the 4 repeater solution, it looks like this weird cup thing. It definitely does not have the symmetry. We can rotate it by 90 degrees and it will look different. And in fact, when you run the optimization, it will randomly output one of these 4 configurations, basically uniformly. Because, of course, they're all equally good. And we can do some more exciting things, where we now look at how good the performance is that we get in the network as a function of how many repeaters we actually put in there. And then we kind of get a figure like this, where things look a little bit like a sigmoid, where at the beginning, we just don't get much performance at all. But then at some point, we hit a minimum number of repeaters, and the performance starts going up with every repeater that we add to the network at that point. But then at some point, it starts to saturate. And in fact, it looks like at some point, it doesn't increase with the number of repeaters at all anymore. And we get to a sufficient number of repeaters. And this makes a lot of sense because repeaters are noisy hardware. So at some point, adding an extra repeater in your network will not be worth it because it will introduce more noise into the network while things are already pretty fast. We already can make containment really quickly because the distances involved are pretty small. And it's just not worth it. So what optimization will do at that point is just say like, oh, this repeater that you gave me, I just don't want to use it. I just put it somewhere in a corner and I'm going to ignore it. And that's sort of why it tapers off. Of course, we're using simulated annealing and Monte Carlo methods, so everything is random, and that's why the results are not super coherent, and things go up and down a little bit, but that's to be expected. And we can depict one other thing, which is the best secret key rate that we get over the optimization, which is just the highest value across all the optimizations we find. So in this case, it's this little data point over here. And we can think of that as sort of the optimal performance that we can, or the best possible performance we can get out of this network, out of this geometry. And then we can do more interesting things with analysis on that, because now we can take the square and we look at the size of the of the edges of the square. Sorry, my throat is getting a little bit sore. Is this safe? So we can look at the length of the edges of the square and make it longer or slower, or smaller, and look at how these different parameters of that we saw in the figure just now, how these evolve. So if you look at the best possible performance that we can get out of the network, and we start making the network bigger and bigger, we see that this secret key rate starts to go down basically exponentially. Well, that sucks, but to be honest, that's not very unexpected with this particular type of quantum repeater that we're looking at, because it's kind of a dumb method of doing quantum repeaters. There's no quantum error correction, there's no fidelity. It's sort of like a 0th generation quantum repeater almost. And this is something you would also get in a quantum repeater chain. If you just make the distance longer, even if you have an infinite number of quantum repeaters, you would be seeing something like this. Something else we can do is looking at sort of this, both the minimum number of repeaters that we need in a network to get anything, and the maximum number of repeaters that we need to get to the best possible performance for that particular geometry. And then we see that both of these numbers scale more or less linearly with the edge length of the square. And I think that's kind of good news, because the edge length of the square is only the square root of the total area of the network. So that basically means that if we make the total network area 4 times larger, we only need twice as many repeaters to do things. So I think that's pretty neat. Maybe a little bit unexpected, maybe not super unexpected if you think too much about it. But I think that's kind of convenient. And this is actually the last result slide I have. So with that, thank you all for listening. Just in time before my throat gives out, so
just in time to ask Hughes a bunch of questions.
Yes.
So, yeah.
So do you know why stochastic AD performs so much better than finite differences? And are you aware of any like other methods for estimating derivatives for Monte Carlo?
Yeah, I mean, so there are other methods like stochastic AD that are similar. Most of these don't work super well if you have discrete randomness in your random function, which is something you have all the time if you do non-quantum networks, because you would try to make entanglements, and it's either going to succeed or it's going to fail, and it's not going to be somewhere in between. So everything is super discrete all the time. So there are things that you can do, but usually they either give you like a pretty large variance, which you can get around with the stochastic AD, or it just doesn't work basically. Or you have to introduce a bias. There are some trade-offs sometimes, but
So thanks for the nice presentation. It seems that everything is like working very nicely at this point. So can you give any ideas of, like, do you have any future projects with this in mind? Are there any other things you want to explore?
So one thing you need to do in order to determine how good the network is like this, like I can give you some node configuration and I ask you how good is this network. In order to do that, we need to find paths through the network also. I want to know if I want to talk with, if I want this node to talk to this node, I need to find a path through the network that fits the number of quantum repeaters to do that. And now I want to know what is the best possible path to the network to actually realize that. And it turns out that is kind of a hard problem in the quantum case sometimes. It has to do with isotonicity. Basically, your path metric is not well behaved, where basically if you're one path going to a node and another path going to that same node, doing your different routes, and the first path is better than the second path, but then you want to go to the next node over, it might suddenly happen that the second path becomes better than the first path. And that breaks everything in classical pathfinding algorithms, like Dijkstra's algorithm. And that really sucks, but it also opens up some interesting space to explore. So that's going to be some next project coming out of this.
Okay. I also have a super quick question about like if you were to consider moving from kind of like these physical networks with like repeaters and everything and start thinking about like needing to deal with error-corrected states, like does the problem look pretty similar? Are there any issues that arise from like making that switch, or do you just kind of like are you able to kind of just make like adjustments to just probabilities of certain operations, or do you have to deal with a lot more?
Yeah, that's a very good question. I think it should be possible to incorporate something like that. But in my simulations, I'm taking a little bit of shortcut where I'm just sampling some numbers and then calculating an analytical function on that. So in some sense, my Monte Carlo simulations are semi-analytical, semi-numerical, I would say. Well, there's also ways to do like a full numerical Monte Carlo simulation where you have a bit more freedom. And then I'm looking, for example, at Stefan, who's doing all the quantum savory, and at Hannah. Because quantum savory really allows you to like simulate every aspect of the network, and you don't need to combine some randomness with some by hand calculated functions. But then incorporating a simulator like that with stochastic AD might be challenging, though I think it will probably be a challenge that would be fun to pick up and might give a lot of advantage. So I would encourage the people in that corner over there to consider that.
All right. Any other questions? I forgot to keep track of the time, but I think we can just thank Hughes again. And then I think we have one last speaker in our session.
There's some reminders that they ask us to submit. Hey folks, the poster session is at 6. And as an extra incentive, if really polished posters from smart people are not enough, there's free food. And there's also a keynote at 4. But we'll be done by then? Yeah.
Also, if you have a poster, you should go set it up at 5 after the keynote in Alumni Hall called Connolly Ballroom. It's the first floor. I don't know if anybody does have a poster. Or if your friend has a poster, they should put up their poster at 5 p.m. in Alumni Hall.
We need to take like 4 minutes.
Oh, okay, great, great.
Yeah. Yeah. So if anybody needs a quick break, you have 4 minutes. Oh, that's why. Okay. Yeah. Right? Usually the if it's played in one morning, it probably would have made it for the rest of the day. That's more friendly. All right. I think we're all back in, almost. Nice. Okay. Well, will Casey tell us about Gausslets?
Yep, Gausslets.
Molecular Hamiltonians and tensor networks. Yeah.
Cool. Hi, I'm Casey. I'm a PhD student in the math department at Dartmouth, but I work with physicists, specifically the Whitfield group, with my collaborator Wisher Wing, which is in the audience, and also James Whitfield. And I will mostly just be focusing, sorry to maybe disappoint people, focusing on the Gausslet and basis set part, but I'll also describe at the end current limitations for actually implementing this in iTensor. So to introduce this, we'll be looking at a new wavelet-inspired basis set that was introduced by Stephen White, which you may know is the inventor of DMRG. and we'll look at the applications of Gauss-Lits for electronic structure. And as review, if you haven't seen this already, if you're not as familiar with quantum chemistry, this is the first and second quantized Hamiltonians for electronic structure under the Born-Oppenheimer approximation. So the first part in the first quantization picture would be your kinetic energy of your electrons. The second would be the nuclear repulsion between your electrons and the nuclei of your atomic system, and the last would be the electron-electron repulsions. I'm sorry, I made a mistake. It's nuclear attraction between electrons and the nuclei. And we also have, if you're more familiar with maybe a second quantized picture too, we also have a second quantized picture of our Hamiltonian as well, and this time framed in terms of the creation and fermionic creation and annihilation operators, where this is written in chemist notation, since that's the one I like to stick with. What are some motivations behind using Gauss-Lits, which are very kind of different basis set from typical basis sets you might have seen in quantum chemistry, familiar with that field. Typically, a big focus on that for molecular systems is this approach called linear combination of atomic orbitals, where the basic idea is, okay, a basis set that may describe an atom well, if we just sum over the different basis sets of the atoms, we could have a good description of our molecular basis set. This is a very different sort of basis set in that it allows for a systematic convergence to something we call the complete basis set limit in quantum chemistry. And one really nice property of this basis set that distinguishes it from a lot of other ones is it actually diagonalizes the two-body interactions. So specifically, if you recall the previous slide, we see these elements right here kind of describe it's a rank 4 tensor of the different integrals you need to perform. For this particular basis set, this actually reduces the number of integrals you need to perform from order n to the fourth to order n to the squared. However, there is a large prefactor that comes because you need to add much more basis sets in order to kind of compensate. You can still also use Gaussian integral formulas since they're still come from a sum of Gaussians. And another nice property that ties into tensor network methods is it's a much more local basis set. So this has potential applications. Well, Stephen White has explored these a little bit, and I'm also trying to implement these in iTensor for tensor network methods like DMRG. And it also, to this point, has not been open sourced. I partly see why, because it's so difficult to reproduce. Being a mathematician, I also think that the mathematical properties of this basis set are really cool. So first, what is a Gauss-Lit? That's the formula on the top. You basically sum these CJs are your wavelet coefficients. You sum over those a grid of evenly spaced Gaussians that have basically are defined on a lattice. They have really nice mathematical properties as well that's described in subsequent work by Stephen White in the nested Gauss-Lit basis set property. Not going to go through all of these. One important one actually is this moment property. So they basically integrate like Dirac delta functions for low degree polynomials, and that's what gives you the two-body diagonalization that I talked about previously. But it turns out that just Gauss-Lits alone on an evenly spaced grid are not enough to describe a molecular system. Specifically, if you're familiar with going back to kind of high school and studying the hydrogen atom, you maybe remember one part of the solution. The hydrogen atom is this e to the negative r, and we call that a Cuss condition around the nucleus. So it's actually really hard to have an evenly spaced grid that accurately describes Cuss. So instead, you need to distort your grid is one approach. This is kind of a little bit like doing a multi-scale kind of resolution analysis, but instead you stick with the same grid instead of making different grids, and you distort your grid in order to kind of adapt to the system that you have. So in particular, if we have just any continuously differentiable map, we can compose that map and include this Jacobian factor so we maintain orthonormality. And from this, we can make a new basis set that is distorted. And I'll show some nice pictures of this. In particular, one nice coordinate mapping to use is this inverse sine H map, which has this density, and this is a really nice map to work with because it approximately drops off like 1/x as you go away from a nucleus. So these are some pictures I made of Gauss slits. So on the right is, you imagine this is a set of basis set. This is a Gauss slit basis set on an evenly spaced grid. And then to the left, this is under the coordinate transformation. You see that the basis functions are now packed more. If we imagine having a nucleus at 0, and we need to describe like the nuclear cusp there, this packs the basis functions more tightly around that nucleus. And then this also is a visualization of a 2D grid. So we're also working with something called a Cartesian product basis set, which is ties really nicely to for implementing in tensor networks. This is the mapping for example, for if we have two nuclei, it's a much more complicated process actually constructing this. You can kind of roughly imagine summing them, but even though that's what they kind of state, actually in some of the papers, it doesn't work quite as well, so you have to do a little bit more complicated procedure. But you can see in this case now, actually my basis functions are packed more tightly around both of my nuclei positions, but I still maintain all the nice mathematical properties I talked about earlier. Another thing to be aware of too, when you're working with this Cartesian product basis set, it's really important because I'm dealing with a ton of basis functions to decompose it as a product of 1D basis functions, and this makes the integrals a lot simpler to work with and manageable, because if everything was kind of mixed together, the integrals would quickly become unmanageable to deal with. So if you're just aware of a basic Gaussian integrals identities, this is actually a really nice way to decompose your Coulomb operator, and this is a really cool trick. Actually, and this is, for example, a test I did of just the hydrogen atom, which is nice to analyze, of course, because we know the solution in atomic units, it's just negative 0.5 Hartrees is the ground state energy. And one really cool aspect about this that we see is that actually nicely captures excited states too, even though I didn't actually state any specific information about the angular momentum. So that's really one really cool thing that pops out of this. Also, you can do like look at the landscape of the possible parameters, and that's one thing we want to work on in the future, is possibly doing automatic differentiation on the parameters of your basis set with using QuickBox, which is the main tool that we'll also talk about at the end, that was developed by Weisher Wing. So in this case, we see actually that decreasing that this bottom square is like the optimal choice for these two core and scaling parameters of your basis set. And this is really nice too, because I have a large number of basis functions, but I've correlated them just to 2 parameters. The iTensor implementation is still a work in progress. There's this package actually called iTensor Chemistry, which it seems which would be really nice to use. However, if you just look at the package, this is the first thing that pops up at the beginning. One thing that we kind of are able to tackle is that we are able, if you see right here, it has typically basis set scale like order n to the 4th for n orbitals. Well, like I said before, now we only have O n squared orbitals. However, now in order to actually tackle realistic systems, I still need to deal with thousands of basis functions. So this is still an ongoing work to actually implement this in DMRG, and particularly constructing the MPO using this basis set is currently feasible. However, there may be there still may be ways to still do this. Obviously, they were able to do this in the papers. So this is still ongoing work to try and have a native iTensor implementation of this. I think you can also take advantage of the locality of the basis set as well to maybe have a more manageable way to construct your MPO. Yeah, and future work is constructing the MPO for electronic Hamiltonian using iTensor, doing parameter optimization using automatic differentiation, which Weisher will talk about on Friday, is you're able to do using his QuickBox package. And in general, I used QuickBox for a lot of these along with my own custom integrals. And this is something you really couldn't do in any other sort of basis set package because QuickBox allows you also to work with 1D basis functions and compose them really nicely as well. And one other thing that would be great to explore was that when is it advantageous to use something like a Gauss-Lit basis set for quantum computing? If you're familiar with quantum computing literature and quantum chemistry, there's always an underlying assumption that they use like a minimal basis set like STO3G. So actually understanding how basis set discretization affects stuff like VQE would also be great to explore. Cool, thank you.
All right, questions for the speaker from the audience?
I don't know if you're aware, but iTensor chemistry is basically no more developed at the Flatiron. So I think if you're interested in taking it, you should like restart it. But right now, no one at the Flatiron Institute is directly working on this precise package.
Oh, okay, that's great. That's great to know.
So yeah, like if you really want to do something, you should consider starting your own package.
Yeah, that's what I realized pretty much. I think there's this other package though mentioned, this iTensor MPO construction that I think will actually be really useful for
We should
constructing the
discuss more about the current state of iTensor then, I guess.
Yeah. Cool, thank you.
Cool. Other thoughts, questions?
Okay.
All right. Well, let's thank the speaker again.
All right. Thank you.
Yeah.
May I
okay.
start?
Yeah.
Or you want to?
Next up, go for it. Yeah.
Okay. So my name is Peter. I am a graduate student both at Purdue University and at the Federal University of Rio, back in Brazil. And today I'm going to give a talk about this package that I am the main developer called Cubo.jl. But this time I'm going to give you an operations research user experience perspective. So what is Cubo.jl? First of all, what is Cubo? So Cubo, as many people here might be familiar, stands for Quadratic Unconstrained Binary Optimization. And it's the main mathematical framework through which many of the quantum devices and also other physics-inspired devices have been communicating. So many of them are capable of addressing this specific mathematical formulation. In a certain case, because it is the simplest non-trivial mathematical model, so to say, because you have only binary variables, you have no constraints, and your objective is quadratic, because if it was linear, it would be too simple. So it can, in fact, encode many types of problems that are known to be NP hard. So this package, Cubo.jl, it has a lot of stuff going on. It has a common interface in JUMP for these many different solvers to be operated. So in a certain sense, allows people to access quantum devices through JUMP. which is super fun. On the other hand, it also allows people to translate more complex mathematical models into the cuboformalism, and then it goes to the device. So this also allows us to do some systematic benchmarking and compilation that is directed to the architecture. So going forward with this, there were many talks about Cubo.gl before, explaining how we can draw parallels between its tools and some other compilation tools and passes and everything that goes behind. We also discussed how mathematically this happens in other jump dev and JuliaCons, and also how this really happens and more advanced things that are going on behind. And also, it's the fastest thing around and one of the most comprehensive tools for doing these things. But today I want to talk more about user experience and a little bit of the history of how Cubo.gl was developed and how we can how we can think about the field as it's evolving and other related tools. So I'm part of the operations research area, and I spent some time in industry, especially working with power systems. And at some point, we started interacting with people who develop quantum hardwares and also people who are into algorithms that are either inspired by quantum or also address the same kind of problems. And in another Thursday in the office, I was thinking about this problem where you have to plan the power plants you're going to build and you have to operate them. And we usually write it down. As you can see here, you have some operation costs, investment costs, unit commitment, and constraints going on. And usually we just write this in Jump, and it's very similar on how you think mathematics and how you write code. And this is something that if you think, if anyone here was in the OR tools talk earlier before, the great thing about mathematical programming is that it's above all a language in which we can express ourselves. You just define problems. You don't care much how they are solved, but people are used to. So whole industries rely on being able to express ideas through mathematical programming. And this company I was working for was very deep into research. Actually is pretty much part of the Jump community still up to this date. And my boss just asked, how can we run this on quantum devices? And ideally, what we wanted to do is that we could change 2 lines of code and be able to run it directly. So this was the dream back then. On the other hand, we started interacting as the project went on, and we started interacting with other companies that were developing all those tools, and we faced a very heterogeneous landscape of devices. So we had quantum machines, we have meteoristics algorithms that were also compatible with the cuboformalism. We even developed more recently a solver that is based on iTensor to use tensor network algorithms for solving cubos. And interfaces usually adopt all different conventions you can think of. Some of them want Ising models, some of them want cubos. They have different installation methods, programming language. Just this part just reminds me of Python interoperability all the time. And you have different data formats. Some of them give you results in an asynchronous manner. Some of them give you that straight away. And on our sides, much of my colleagues that were not that much interested in quantum or learning about it, it was just too much, right? So this is where really Cubo.gl stands out. So we were able to get all those things that were going on and organize them very straightforwardly into Jump. And suddenly you had complete access to all these devices in the same manner that you used to do before with your regular solvers, let's say Gurobi or Hive or something in that sense. So now we have the same interface. You write the same code for D-Wave, for IBM machines, for parallel tempering algorithms, and new machines were dropping. As the project was evolving, new devices came up, and we were able to rapidly integrate them because if for the user, it's now very easy because they're used to running models in JUMP this way. For algorithm developers and hardware manufacturers, the code for integrating this into the JUMP ecosystem was just this. So this is actually the real code, the one that is being used for the D-Wave integration. And you have a macro to set up all the math-opt interface boilerplate and some other code telling you how to sample those results and organize them. And that's it. So this is all you need to have your solver integrated with JUMP. Naturally, as soon as you have this whole collection of solvers that we could use right away, testing them automatically and benchmarking them was just the next step. So we came up with a library for organizing all these instances of different Kubo problems, and this led us to a partnership in the IBM Quantum Optimization Working Group that led to a paper, to another benchmarking library. So in this sense, it was very successful. And everyone was happy, right? So both device developers and people who are used to just setting attributes and calling optimize were now all able to access quantum machines. And we delivered some summer courses on this in different universities, and students, they just got their API keys and just started running the models. They have, if you just search for Kubo notebooks, there are many notebooks that make using quantum devices as easy as this. So in summary, we started with our goals were just to have a common interface and a compiler that allowed us to run more complex problems, such as the one for operating power plants. And this led us to some questions forward. So how can we pick the right solver, and how can we choose the best way to reformulate a problem? And this led us to benchmarking, and benchmarking led us to have a library. And currently, we are giving our steps beyond Kubo, because this whole thing of having an interface that makes it so user-friendly and accessible, I would say. And more than that, when people usually think of optimization as being a killer app for quantum and something that people say it's going to be advantageous as soon as possible, and that should be something people should be interested into, and we look at how people actually do optimization out there, the interfaces, they are very, very apart. So if you look at the regular pipeline for operations research and how you expect your problem to be passed and results to be analyzed later, there is a gap in between that keeps experts in the field from really thinking about this problem and how to use novel devices. So as soon as we started bridging this gap with our software and got more and more attention, we also went beyond Kubo, and some manufacturers that develop hardware that are capable of not only binary but also integer and misinteger problems also approached us. And this led me to do some internships that in other companies that were interested in this, and this led us to an expansion and made also our Kubo tools way better. So what I wanted to say in the end is that for optimization to really be something, and for us to understand the relevant problems that need to be benchmarked, we need to get closer to the community that has been doing this for a long, long time. Because much other problems that we usually see as being the ones that are first approached by quantum are very classical computer science problems, so to say. And I feel, so this is the take I want to get with this presentation, is that we should be closer to people doing the applications that move very heavyweight industries all around. So I would like to thank my collaborators that started the project at PSR and at the Federal University at Rio, and now that still work with me at Purdue University. And my colleagues at Microsoft that were responsible for taking this project also to other formulations and to the machine that they've been developing. That is a photonic machine that's quite interesting, and for being such supporters of Julia and using this in the whole pipeline of the novel machine that they brought up. Thank you.
I think maybe for sake of time, we should maybe have questions offline. We could do like maybe one quick question and then, yeah.
Were there any machines on which, quantum machines on which these actually were executed and showed something that was better than the best classical tools in JUMP?
So, sorry. Okay, the benchmarks. So the benchmarks, they were run only in comparison, so they all use JUMP, because what happens that most of the benchmarks that we've seen before, they were from a single manufacturer on a single problem or just a few problems, and they're like highly biased towards either problems that are well-known in literature or the ones that work very well. And with this work, we are able to put this benchmarking up to scale in two senses. One, that we have one of the strongest reformulators in the market. So in this IBM paper, we were able to generate very large instances and different instances of different types. And in the other sense, since they're all connected to JUMP, we don't have the same situation where you have a paper with two different devices competing. We now have dozens of devices competing. So, but this is not focused on, at least not talking the reformulation side, on getting the best of the performance of the solvers. We're providing the way for hardware developers and algorithms people to basically fight each other under a common ground.
But the quantum folks, did they win anything in that fight?
No,
the quantum folks, did they win anything in that fight?
I have no news about that, yeah. Like, never heard of any quantum really winning. I think, yeah. But something that's very important, and we cannot just underestimate that, is that great advances in the hardware side have been happening over the past like 5 years. The advances are great, and this is a very nice way to keep track of how things are evolving with time. Like the amount of data that we generate at each time slice that we run our benchmarks is the coolest part of it.
All right. Well, I think at this point, we'll take any extra questions offline, and we can thank all the speakers for the session. And I think this closes all the quantum talks. So yeah, big round of applause to everybody who's here for all the quantum talks. All right, you got about 10 minutes, I think, before the, like 4:10 or something like this. It's like just after, yeah. So you got a tight window. So.
Yeah, so it's in the same building. It's in the same building.
Oh, okay. Yeah, same room as all the others. So the big main room for the next large talk.
Also, just before everyone goes, tomorrow there is a quantum chemistry and material science mini. Might be interesting as well.